Good afternoon all. Myself Tilak Pandya, PhD Research Scholar at Department of Physics, Saurashtra University, welcomes you all on this platform named Vigyan Yatra, a travel for scientific Indian minds towards the Vikshit Bharat. Vigyan Yatra is a series of conference sessions from March 4th to 15th, 2024, and it's jointly organized by the Department of Physics, Saurashtra University, RAJKOT, Vigyan Gurjari, Gujarat Prant Unit of Vigyan Bharati VIBHA, GUJCOST, Department of Science and Technology under the Gujarat Vigyan Sammelan 2024. We are honored to have with us Sri Vivekanand Pai, National Secretary, Vigyan Bharati VIBHA, Professor Atul M. Gosai, Professor at Department of Computer Science and Member, Board of Management, Saurashtra University, Rajkot. We are extremely grateful to our patrons and co-patrons, Professor Nilambari Dave, Honorable Vice Chancellor, Saurashtra University, Professor Chaitanya Joshi, President, Vigyan Gurjari, Gujarat Prant, Dr. Narottam Sahu, Honorable Advisor and Member Secretary at GUJCOST, Gandhinagar, Dr. R.G. Parmar, Registrar at Saurashtra University. I heartily welcome our today's invited speakers, Dr. Narendra Jakhar, Assistant Professor at Department of Physics, University of Rajasthan, Jaipur, Dr. Archana Lakhani, Scientist G, UGC-DAE Consortium for Scientific Research. I also welcome Professor Nikesh Shah, Professor and Head of Department of Physics, Saurashtra University, Professor P.N. Joshi, Secretary, Vigyan Gurjari, Saurashtra Prant, Professor J. Phalodia, Professor at Department of Physics, Saurashtra University, Professor K.B. Modi, Professor at Department of Physics, Saurashtra University, Professor H.O. Jetwa, Professor at Department of Physics, Saurashtra University, Dr. Phy-SU Solanki, Assistant Professor at Department of Physics, Saurashtra University, Dr. David Dhruv, Assistant Professor at Department of Physics, Saurashtra University, Dr. Megha Wagadia, Assistant Professor at Department of Physics, Saurashtra University, and all the participants. Moving ahead, I request Dr. Phy-SU Solanki sir to welcome and introduce us to today's guest. Dr. Phy-SU Solanki sir is Assistant Professor at Department of Physics, Saurashtra University, and Coordinator of Science Club, Saurashtra University.
Yeah, so thank you, Mr. Tilak. Let us welcome today's speaker, special guest, and all the participants. So start with our special guest, Sri Vivekanand Pai sir. On behalf of this Vigyan Yatra, we are welcoming you to this online platform as a part of Saurashtra University, Rajkot. The Sri Vivekanand Pai sir is a National Secretary of Vigyan Bharati, VIBHA. This other special guest is Professor Atul Gonsai. Professor Gonsai sir is a professor at Department of Computer Science, Saurashtra University, Rajkot. He has achieved 13 awards and achievements during his tenure of academic projects. Almost 10 major and minor projects have completed and ongoing. 80 plus publications he has, and more than 70 talks he has delivered at different national and international events. So both of you, sir, you are most welcome to this event. Thank you very much. Yeah, so I would like to invite Sri Vivekanand Pai sir. Please give your words as a blessings to these events and all the participants.
धन्यवाद पीयूष जी.
Moving towards the
Yeah, Pai sir, you are mute.
Yeah, just a minute.
Yeah, no problems.
I just forgot to insert my. Can you hear me now?
Yeah, sir, voice is too low.
Can you hear me now?
Yes.
धन्यवाद पीयूष जी और आदरणीय प्रोफेसर अतुल गोसाई जी,
नमस्कार, राकेश शाह जी और आज के जो वक्तव्य देने वाले नरेंद्र जाखर जी, अर्चना जी और बाकी सभी वरिष्ठ लोगों को नमस्कार और इस कार्यक्रम में जुड़े हुए बाकी सभी लोगों को अभिवादन करता हूँ। आज ये बहुत हर्ष की बात है एक बार फिर गुजरात के कार्यक्रम में जुड़ने का। पिछले साल भी जो गुजरात विज्ञान सम्मेलन का अंतिम कार्यक्रम हुआ था उसमें जुड़ने का मुझे सौभाग्य मिला था और आज एक बार और गुजरात विज्ञान सम्मेलन के इस विज्ञान यात्रा में जो कि सौराष्ट्र यूनिवर्सिटी, विज्ञान गुर्जरी, गुजकॉस्ट और डीएसटी गुजरात मिलकर करते हैं और ये एक बहुत सराहनीय कार्यक्रम है। इतने 9 दिनों में इतने सारे लोग आकर विज्ञान के एक एक प्रकार से जो लेटेस्ट डेवलपमेंट्स है उस पर वक्तव्य दे रहे हैं। मैं चंद मिनटों में विज्ञान भारती का एक परिप्रेक्ष्य इसमें बताऊंगा। विज्ञान भारती लगभग 30 साल से ज़्यादा अब वैज्ञानिक जगत में काम कर रही है और ये एक स्वयंसेवी संगठन है। एक प्रकार से भारत का सबसे बड़ा वॉलंटरी प्लेटफॉर्म इन साइंस एंड टेक्नोलॉजी। हमारे पूर्वकाल अध्यक्ष थे डॉक्टर विजय भटकर जी, जिन्होंने भारत के लिए परम सुपर कंप्यूटर का डिज़ाइन किया था और आज हमारे अध्यक्ष हैं डॉक्टर शेखर मांडे जी, जो कि सेक्रेटरी डीएसआईआर एंड डीजीसीएसआईआर थे और एक प्रकार से डॉक्टर अब्दुल कलाम से लेकर डॉक्टर माधवन नायर तक सब लोगों का विज्ञान भारती के प्लेटफॉर्म पर आना, विज्ञान भारती से जुड़कर एक न एक कार्यक्रम में भाग लेने का हमें सौभाग्य मिला है। और विज्ञान भारती मूलतः 3 बिंदुओं पर काम कर रही है। एक है विज्ञान जगत में भारत का योगदान प्राचीन से पौराणिक काल से लेकर आज आज के दिन तक। इंडियन कंट्रीब्यूशन टू साइंस, इंडियन हेरिटेज इन साइंस फ्रॉम एंशिएंट टू मॉडर्न। एक प्रकार से हम कहते हैं कनाडा टू कलाम, एक सिंबॉलिकली इसका अलग अलग ये होते हैं फिर भी। और दूसरा है विज्ञान और अध्यात्म की जो भावना है भारत में। आज मटेरियल साइंस पर वक्तव्य शायद आ रहा है और कल ही हमारा तो माननीय प्रधानमंत्री ने प्रोटोटाइप फास्ट ब्रीडर रिएक्टर का कोर लोडिंग का ये किया था कल्पाकम में। हम वैज्ञानिक जगत में बहुत आगे गए हैं। एक प्रकार से जब भारतीय सोच इस पर देखती है तो 2 प्रकार से देखती है। एक है कि जो फिजिकल साइंसेस हैं, फिजिक्स, केमिस्ट्री, मैथ्स, बायोलॉजी, बाकी आज जो भी हम दिखते हैं और देखने की कोशिश करते हैं फ्रॉम मैक्रो टू माइक्रो। आज हम जानते हैं कि डीएनए फिंगरप्रिंटिंग की जगत है और एक डीएनए मिली। अगर हमने एक हैंडल पर भी मुझे एक अवसर मिला था हैदराबाद में सीडीएफडी में जाने का, तो उन्होंने कहा कभी-कभी ऐसा अवसर आता है कि किसी ने एक हैंडल पर एक कोई क्राइम हुआ है, हैंडल पर पकड़ा था, वहाँ से हमें डीएनए मिलती है, उससे उसका पूरा एक एक चित्र हमें ले सकते हैं। उस समय जब हम गए थे उस समय ये जेनेटिक इंजीनियरिंग बिल का पास नहीं हुआ था। आज वो भी पास हुआ है, इसके लिए इसको स्टैट्यूटरी एक्सेप्टेंस भी है। और जो आधुनिक विज्ञान है इस प्रकार भीतर आज हम बोसोन की लिए जो देख रहे हैं उसके भी मैटर, मॉलिक्यूल्स, देन एटम्स, न्यूट्रॉन्स, इलेक्ट्रॉन्स, प्रोटॉन्स, सबएटॉमिक पार्टिकल्स, ऐसा जाके फोटॉन्स, आज बोसोन्स, इस प्रकार जाके इस जगत के बारे में समझने की कोशिश कर रहे हैं। और इसके साथ साथ बहुत सारे तकनीकी ये आगे जा रहे हैं। जैसे हमें इलेक्ट्रिसिटी मिल रही है, ट्रैवल हो सकता है, बाकी सब आज इतना आईटी जगत में आगे गए हैं। आज आर्टिफिशियल इंटेलिजेंस की बात हो रही है। पर ये एक बात है, इसे हम एक प्रकार से अविद्यया मृत्युम कीर्त्या विद्यया अमृतमश्नुते ऐसा कहेंगे। तो एक प्रकार से जो मटेरियल साइंसेस है इसे हम अविद्या कह सकते हैं। पर भारत की एक सोच है कि ये पूरा जगत कैसे इसकी सृष्टि हुई, उसका क्या कारण है। एक प्रकार से हम देखेंगे तो मैं कहता हूँ मैं, तो हु एम आई, इसकी भी सोच हुई है। और इसका एक सामंजस्य का एक चित्र भारत के फिलॉसफी से आया है। उसे हम स्पिरिचुअल साइंसेस कहते हैं। और एक प्रकार से हम जो आर्टिफिशियल इंटेलिजेंस कहते हैं, उसके इंटेलिजेंस, जो इंटेलिजेंस कंपोनेंट है, उसका आधार क्या है। एक प्रकार से दैट इंटेलिजेंस इज डिपेंडेंट ऑन समथिंग विच इज कॉल्ड कॉन्शियसनेस, and that consciousness is dependent on something called universal consciousness. That universal consciousness is the creator of whatever we see. ब्रह्म सत्यम जगन मिथ्या, जीवो ब्रह्मैव ना परा, ऐसा जो शंकराचार्य ने कहा। इस प्रकार भारत की सोच है। इस कारण से अविद्या मृत्युं तीर्त्वा विद्यया अमृतमश्नुते, ऐसा जो अमृतमश्नुते मीन्स दैट एटर्नल ट्रूथ जो समझने का कोशिश है, वो भारत का एक योगदान है। और इसको अगर पकड़ के हम आगे जाएंगे तो एक प्रकार से आज की जितनी भी समस्याएं हैं, उसका समाधान मिल सकता है। क्योंकि फॉर अस, आई एम नॉट डिफरेंट फ्रॉम माय सराउंडिंग्स, आई एम नॉट डिफरेंट फ्रॉम माय other colleagues, I am not different from anything. There is a unity among everything. ऐसा एक सोच आता है। तो इस प्रकार से हम जो जो पृथ्वी का भी आज इतना क्लाइमेट चेंज, इस प्रकार से बहुत सारे मसले आते हैं, इस प्रकार की सोच में भी नहीं जाएंगे। क्योंकि देर इज नो साइंटिफिक और टेक्नोलॉजिकल सॉल्यूशंस टू मेनी ऑफ दिस इश्यूज। इट इज मच मोर ऑफ ए फिलोसॉफिकल अप्रोच दैट इज कॉजिंग द क्लाइमेट चेंज। आज अमिताभ घोष का पुस्तक है नटमेग्स कर्स, उसमें उन्होंने बहुत ही सुंदर तरीके से बताया है कि जो वेस्टर्न फिलोसफीज एंड ईस्टर्न फिलोसफीज ऑफ लुकिंग एट रिसोर्सेस, ये कैसे अलग अलग होता है। इसकी एक बहुत ही सुंदर कहानी भी उन्होंने इस पुस्तक में दिखाई है। तो इसमें कहा जाता है कि जो हमारे अपने ये पर्वत होते हैं, नदियाँ होती हैं, जो पेड़ पौधे होते हैं, जो ईस्टर्न फिलोसफी है उसमें इट इज अ पार्ट ऑफ आवर फैमिली। वी डोंट लुक एट इट एज ओनली एज रिसोर्सेस, वेयरएज द वेस्टर्न फिलोसफी लुक एट एवरीथिंग एज रिसोर्सेस। इसके कारण ये आज इतना इट इज उनका कहना है कि एक प्रकार से क्लाइमेट चेंज इज ए कॉन्ट्रीब्यूशन ऑफ द कॉलोनियलिज्म। ये एक बहुत ही सुंदर पुस्तक उन्होंने लिखी है। तो ये सोच हमारी दूसरी एक बिंदु है। और तीसरी बिंदु है कि विज्ञान भारतीय भाषाओं में। और अ, इसका हमें एक एक स्वरूप दिखने को मिला जब हमारे जो फाउंडर हैं प्रोफेसर के वासु, एंड ही फाउंडेड विज्ञान भारती ड्यूरिंग द 80s, एंड इट स्टार्टेड लाइक दिस। वो इंडियन इंस्टीट्यूट ऑफ साइंस में फैकल्टी थे। और 2018 में उनकी नवति के अवसर पर उनका जहाँ इसका प्रारंभ हुआ वहाँ जाने का हमें अवसर मिला। एंड एट दैट टाइम वो दैट यूज्ड टू बी ए लाइब्रेरी, and he used to sit there, and there was an opportunity for the at IISc to learn all the foreign languages. So he thought, he came to know that there are many texts in Sanskrit on science। तो इस कारण से उन्होंने सोचा कि फॉरेन लैंग्वेजेस के बजाय मैं संस्कृत पढूं। और उन्होंने उस समय के आईएएससी के अधिकारियों से पूछा, क्या मुझे संस्कृत पढ़ने का, इंस्टेड ऑफ लर्निंग से फ्रेंच और जापानीज और जर्मन और अनदर लैंग्वेज, कैन आई लर्न संस्कृत। तो उस समय भी इसकी सुविधा आईएएससी में नहीं थी। मुझे नहीं लगता है कि आज भी वो सुविधा है। उस प्रकार से उन्होंने फिर संस्कृत संघ से संपर्क किया और उस प्रकार देखा तो उनको समझ में आया कि पराशर सरणी है, पराशर का जो ये भरद्वाज संहिता है, इस प्रकार से बहुत सारे पुस्तक हैं जिसमें भारत का वैज्ञानिक जगत में योगदान, इस पर बहुत सारा एक ट्रेजर हाउस है। भाषा के कारण हमें ये प्राप्त नहीं है। उस प्रकार से उन्होंने इस पर सोचना शुरू किया। और विज्ञान भारती एक प्रकार से द स्वदेशी साइंस मूवमेंट ऑफ इंडिया ऐसा करके उसी सोच के आधार पर इसका फॉर्मेशन हुआ। ड्यूरिंग द 80s 89 में केरला में इसका शुरुआत हुई। 91 में राष्ट्रीय स्तर पर ये शुरुआत हुई। और आज इसकी इकाइयाँ जैसे विज्ञान गर्जरी इसका गुजरात चैप्टर है, उसी प्रकार केरला में स्वदेशी शास्त्र प्रस्थानम है, तमिलनाडु में அறிவியல் संगम है, बंगाल में विवेकानंद विज्ञान मिशन है, आंध्र प्रदेश में भारतीय विज्ञान मंडली है, और विज्ञान भारती इस रूप से विदर्भ में, दिल्ली में सब है। तो इंद्रप्रस्थ विज्ञान भारती है। इस प्रकार देश के हर प्रांत में आज इसकी रजिस्टर्ड यूनिट्स हैं और बहुत सारे कार्यक्रम भी कर रहे हैं। एक प्रकार से जो स्वदेशी साइंस ऐसा हम कहते हैं, साइंस इज यूनिवर्सल पर इट हैज इट्स द यूनिकनेस ऑफ इट्स ओरिजिन। एक प्रकार से हम कहेंगे तो इंटरनेशनल योगा डे, yoga is a universal thing, but we can say that it originated from India and it has unique impressions of India. तो जैसे योग है, आयुर्वेद है, और मैथमेटिक्स में जो भारत का योगदान है, एस्ट्रोनॉमी में है, आर्किटेक्चर वास्तुविद्या में है, तो इसे हम स्वदेशी साइंसेस कहते हैं। एक प्रकार से स्वदेशी साइंस मूवमेंट ऑफ इंडिया विज्ञान भारती है और इसका गुजरात में भी अब बहुत बड़े पैमाने पर कार्यक्रम हो रहा है। भारतीय विज्ञान सम्मेलन पिछले दिसंबर में अहमदाबाद में हुआ था, मुझे भी वहाँ आने का भी अवसर मिला था। तो मुझे ये बहुत ये हर्षदायक है कि इतना बड़ा एक कार्यक्रम अभी 9 दिनों में ये विज्ञान यात्रा और उसके बाद भारतीय विज्ञान सम्मेलन संपन्न हो रहा है। इसके लिए मेरी पूरी बधाइयाँ और आज जितने भी लोग इसमें भाग लेते हैं उनका भी अभिवादन करते हुए मैं अपने शब्द वाणी को विराम देता हूँ। नमस्कार।
Thank you very much, Vivekanand ji, for introducing the science from the basic level of Rashtra and the Sanskrit, and you have provided various aspects and different, ayams of this science. So one can realize the science from so many aspects, and the most important is the basic Rashtriya aspect, as I can say. So thank you very much, sir. Now let me welcome Professor Atul Gunsai, sir, to share your views about our campus ongoing online sessions. So please, sir, Atul sir.
Okay, thank you, Dr. Piyush, and all the esteemed guests, particularly Vivek Pai ji and the Professor Nikesh Shah, the head of the department, as well as the president of Vigyan Bharati Saurashtra Prant, Piyush Bhai, Jointly by Balodia, and different online ignited minds. I am using the word ignited minds because these all are joined from various parts of the country. As I see the number that about more than 600 participants has registered for this Sammelan. I use the word Sammelan or lecture series, Vigyan Yatra, and about 18 states are covering and about 5 union territories. So we should say it's a national event, and I congratulate the Department of Physics entire team, starting from the captain Nikesh Shah, Piyush Solanki, Jayanti Bhalodia sir, and not only the Department of Physics, but I also want to thank our Honorable Vice Chancellor, the Chief Patron, as well as the Dean of the Science Faculty, Dr. Bhimani sir, as well as the GUJCOST member, as well as Vigyan Bharati, that all have come together under the one umbrella to ignite all the scientists throughout the country. And once we want to join together with this such event, we want to make our Bharat Vikshit Bharat as per our the Narendra Modi sir's dream. And this all ignited minds out of 100, out of 600. Currently, I am able to see 115 online users. These users are from the different part. They are the undergraduate, faculty members, seasoned researchers. All are here. So I welcome you all in the Saurashtra University in the online mode. But if we get a chance in future, we are planning to take you all to the Saurashtra University, the land of the Saurashtra is famous for the hospitality, and we will definitely uh, host you all in physical mode if we get a chance. So I welcome you all because I am also from the Saurashtra University, but my area is a computer science, and Piyush Solanki has already said that most of the work I am doing in the computer science. But the way this Vignan, the science is contributing, is a foundation. Without the science, we are nothing. And whatever you are seeing in the current modern world, that is only because of science. So I am very happy that Vigyan Yatra 2024, this is a conference series jointly organized by the Physics Department, GUJCOST and Vigyan Bharati. This is the collaboration under the umbrella named Gujarat Vigyan Sammelan 2024. This is showcasing the efforts of various institutions toward the advancement of science and technology. And I would like to say this all heterogeneous group. Nowadays, we are also seeing the heterogeneous group named STEM, STEM. So now science is not only one, but the certain brothers are also joining the main foundation science. So the other science brother are the science, technology, engineering, and mathematics. This STEM is nowadays going to make our Bharat as a Vikshit Bharat and Samruddh Bharat and developed Bharat. So this heterogeneous group has to come together, and once we come together, sharing our ideas and sharing our knowledge will definitely ignite the minds for the betterment of our society. Even we can see that physics department is also wondering the things, and I can see physics has given a lot of contribution to my computer science field, ranging from chip making, nanotechnology, or simulation, and a number of things, electronics, photonics, signal processing. So there are a number of things that we have developed our theory from the basic science, and that's why the science is considered to be a foundation stone, and three brothers are helping to make our country develop. I very proudly want to say that science is also making its own roots and developing our country parallelly. Information technology and technology, that is also dominating the entire world with the foundation of India, our Bharat. As we know that about more than 70% information science technologies are from India, our Bharat. So we are also taking proud, and in the science and technology, engineering and management. Yesterday, our Honorable Narendra Modi sir has inaugurated one under river tunnel. So that is also a brilliant example of science, technology, engineering, and mathematics. So we are not only doing the things, but parallelly all together are making our country proud as well as developed. And nowadays you see the STEM is playing a major role. I'm using all four words together. That is a STEM. Short name is a STEM, and this is ranging, giving the major role. If you see in the modern day, the mobile in your hand, that is also a science, and smartphone is the science. Medicine you take is also a STEM product, as well as if you drive a car, that is also a STEM product. So everything what you think and what you see nowadays, that is all about the science, and the science is creating the wonder with the help of STEM. So today in this session, all ignited minds better think about the collaboration, joint work to make our think out of box, and think out of box will create a new innovation, and that new innovation will definitely lead to developed country like our Bharat. And we are also honored to have a different speakers, including the renowned speakers. I see the list of the speakers in this series that is being started from the 4th March to the 15th March, and about 18 speakers daily going to deliver 2 sessions. So it is a wonderful arrangement by the Professor Nikesh and his team. And in this session, they are definitely going to ignite the different minds and discuss the about the investigation and interdisciplinary research areas aligned to the global priorities outlined with our national Educational Policy 2020. So we want to get certain fruits out of this session, out of this series, and that fruits will definitely make our country proud. And I would like to say in the few words that the journey with of Vigyan Yatra 2024, that will symbolize our collective commitment to nurturing the scientific curiosity of all the online users. I use online participants. These participants might be a researcher, PhD student, faculty, or any undergraduate students also. That will definitely foster the innovation, propelling India towards the bright future. By this word, I would like to say each and everyone for giving me opportunity to speak in front of you as a pure science people. But I am saying that STEM will also include, and this will give a good benefit. I thank Professor Nikesh Shah as a president as well as head of the department of the physics department and his team. I also thank our all patrons and co-patrons of this event. I also thank the Vigyan Bharati, Vigyan Gurjari. And this way, I would like to say Namaskar and Jai Bharat.
Yeah, thank you, Professor Atul sir. Personally, I strongly agree with you that out of the four brothers, STEM, any single brother cannot generate anything nowadays at global level. So, for the fruitful outcomes, it is necessary to all together we have to develop something for the country. Now, thank you very much for joining us and provide your views about our event. Thank you, sir.
Now moving towards the technical session. Now I request Professor J. Phalodia, Professor at Department of Physics, Saurashtra University, and Head of CMR HTSC Multiferrite Lab at Department of Physics, Saurashtra University, to chair the technical session.
Hello. So, I think I am audible. First of all, I would like to thank the organizers. They have assigned a duty, most important duty, as a session chairman. So for today, I think this is the fourth day of this journey, no? So in this journey, we will have today, we will have two speakers. One is Dr. Narendra Jakhar, and another, she is from CSR Indore, Archana Lakhani. So, first of all, I would like to introduce or about Dr. Narendra Jakhar. Hello. So, Narendra Jakhar is a young faculty member at University of Rajasthan. His MSc and PhD both are from University of Rajasthan, and his expertise in the field of condensed matter physics with reference to special topics like electronic structure, magnetic properties of materials, radiation physics, etc. Before joining at this University of Rajasthan, he has the work experience in Oil and Natural Gas Corporation Limited, which is at Mehsana. There he has worked as scientific officer. He has received some honors and awards also. One of them is TAIR Fellowship in 2021 from DST Sub. He has also completed one research project that is on structural and magnetic properties of tubular alloys. He is holding some membership also in Indian Association of Physics Teachers, means IFPT. He is life member of this IFPT and Neutron Scattering Society of India. He has published more than 17 research papers, and today's his talk title, that is X-ray photoelectron spectroscopy It is known as XPS, which is as a probe for surface chemistry of materials. So now, with the permission of organizing committee and head of the department, I would like to call Dr. Narendra Jakhar for his expert talk. Dr. Narendra Jakhar, please.
Yes, sir. Hello, am I audible, sir?
Yes.
Thank you very much, sir. All respected Vivek Pai, sir, Professor Atul, sir, Professor Nikesh Saha, sir, Professor Jain, sir, Professor Devraj Singh, sir, Dr. Piyush, sir, Professor KB Modi, sir, and many more respected professors, faculty members, students, and my also Dr. Archana Lakhani ma'am. So thank you very much for this nice introduction, Zain sir. First of all, I would like to congratulate the whole organizing team of this Vigyan Yatra, especially Professor Nikesh Saha sir, President Vigyan Gurjari, and Department of Physics, Saurashtra University, for organizing this beautiful conference. Actually, you are utilizing the advantages of online mode. I have seen the number of speakers from the different disciplines and different areas. You put them together for your students, and this shows that a lot of efforts have been put in this. Actually, as a science academicians, as a science teachers, we also have this responsibility to attract young minds and young bloods in our field also. And I'm definitely sure that the Vigyan Yatra will surely able to fulfill this dream and fulfill this job. I would like to tell Professor Nikesh Sahaji and Professor Atul Gosai sir that recently we have also organized Rajasthan Vigyan Mahotsav in Rajasthan in collaboration with Vigyan Bharati VIBHA, and this is on the grand level, and the University of Rajasthan is one of the integral part of that program, and Vigyan Bharati, Siri Pilani and DST Government of Rajasthan jointly organized this event, Rajasthan Vigyan Mahotsav. So and today I'm very happy to share the online stage with you all people in Saurashtra University, Gujarat. Actually, I have a long associationship with the Gujarat. As Jain sir told that I have started my career as a geoscientist from ONGC in Mehsana, Gujarat. And I got immense love and support. I got everything from there. So Gujarat is my second home. And still, although I am in the online mode, we all are in the online mode, but still I can feel the warmth welcome from you all people here in Rajasthan also. So with this, I would like to take the permission from the Jain sir that whether I'm going to share my screen, sir.
Okay.
Okay.
You can talk now,
Yes,
sir.
sir.
You can talk.
Okay. Okay. Thank you.
Yes, you can share.
Right, sir. Is it visible?
Yes, yes. You can run the
Okay,
PPT.
yeah.
Yes.
So today we are going to discuss about X-ray photoelectron spectroscopy, XPS. It is one of the finest tool available for the probing surface chemistry of materials. The material surface is the point of interaction. Why? Actually, I know that various different students are also attending this talk from the graduation to the post graduation to the PhD and young faculty members also. So I would like to attract their attention that why we are interested in to study of X-ray photoelectron spectroscopy, because the material surface is the point of interaction or the point of contact with the external surrounding or with the external materials, and therefore many of the problems associated with the modern materials can be easily solved only by the understanding of the physics and chemical interactions that occur on the surface of or the interfaces of the materials layer. And there are various different options available like XPS, ISS, ion scattering spectroscopy, RILS, UPS, and AES. But we are today I'm going to talk on or discuss on this X-ray photoelectron spectroscopy. Okay, so these are the contents of this presentation. First, we will take a little bit brief introduction. 1 second. Okay. And then we will try to look into the history and background of this XPS, because different and many scientific contributions are there in this sophisticated instrument. And then we will try to look into the basics and working principle, followed by the instrumentation of XPS, that what are the different parts of the XPS and why they are used, and how can we take the advantage to understand them, to analyze the data, and then followed by the data analysis and the conclusion part. So X-ray photoelectron spectroscopy, also known as electron spectroscopy for chemical analysis, is a technique for analyzing the material surface chemistry. XPS can measure elemental composition as well as chemical and electronic state of the atoms within a material. I would like to give a pause here. Elemental composition by means that what different elements are present in the surface of my sample, and the chemical and electronic states of the atoms can also be known by this XPS spectroscopy. XPS spectra are obtained by irradiating a solid surface with a beam of X-rays. As our name suggests, that X-ray photoelectron spectroscopy, we actually incident X-rays on our specimen or sample, and then the photoelectrons are ejected out. So this is the process, and the name came from there, X-ray photoelectron spectroscopy. So XPS spectra are obtained by irradiating a solid surface with a beam of X-rays and measuring the kinetic energies of those ejected electrons that are emitted from the top 1 to 10 nanometer of the materials. Here I put this in the bold line, underline, the 1 to 10 nanometers only. Okay, so you can say that this is the limitation of XPS. I can accept, yes, you can only probe the 1 to 10 nanometer of the surface from this, but recently in the further advantages of the XPS instruments, now we can also go beyond this 1 to 10 nanometer depth by this etching of the surface. A photoelectron spectrum is recorded by counting ejected electrons over a range of kinetic energies, and the energies and intensities of the photoelectron peaks enable identification as well as the quantification of all surface elements except hydrogen. So this slide actually shows different chronologies that lead us to the development of different sophisticated instruments like XPS. So it all started from the Röntgen in 1895 by the discovery of X-ray. And this shows the very famous and so-called first X-ray photograph of, and this is the hand of Mrs. Röntgen, and you can see that she is wearing a ring in her ring finger. And then later, 1897, J.J. Thomson discovered electron, and because X-rays, electrons are the integral part of this XPS. And then later, at the 1887, Hertz first reported photoelectric effects. Actually, Maxwell gave the electromagnetic theory, but it was totally theoretical. So Hertz was trying to demonstrate experimentally the electromagnetic waves. So this is the famous Hertz experimental setup, in which there are two electrodes. He applies some voltage difference between these two electrodes and try to produce the electromagnetic waves from these two electrodes. But in between, what Hertz observed, that whenever we fall or incident ultraviolet light on one of this electrode, then what he observed is there is spark is very frequent, but he could not able to continue this observation further. And then later on, Leonard and Holbosch do this experiment again and again and came to some conclusions. But still, classical physics was not able to explain the phenomena of photoelectric effect. And later, 1905, the great scientist of 20th century, Einstein explained the theory of photoelectric effect on the basis of photons is the energy quanta. And that's why Einstein got the Nobel Prize for the explanation of photoelectric effect. And later, the different atomic models were provided by the scientists like Bohr and Rutherford, that how electrons are arranged outside this nucleus. Later in 1920s, H. Robinson, a former colleague of Rutherford's and an XPS pioneer, wrote at that time that an accurate knowledge of the energies associated with the different electronic orbits within the atoms is very essential for the further development of the theory of atomic structure. So he assumed in the 1920 that the binding energies of the electrons in which they are sitting around the nucleus is very essential to know about more about the atomic structures. And later in 1954, Swedish physicist Seiben's group built the first high-resolution system for XPS, which they prefer to call electron spectroscopy for chemical analysis. And for that, Seiben awarded Nobel Prize in 1981. With this, now in this slide, we are trying to see the basic and working principle. We say that the sensitivity of the XPS is limited to the depths of only 10 nanometers beneath of the object surface or the specimen surface. Why it is so? What is the problem with the, we could not go on the longer or deeper depths than 10 nanometers or beyond this 10 nanometers? Is there problem with the X-rays that they cannot able to penetrate in the specimen more? No, this is not the problem with the X-rays. X-rays, here it can written that X-rays penetration depth is 1 micrometer. It also depends on surface to surface, but a rough idea is what 1 micrometer means. X-rays, if this is the specimen, your specimen, then X-rays can penetrate in this region here, right? But we can only get the information from the only very narrow region from only 10 nanometers. Why it is so? When X-rays are going there in very deeper distance into the specimen, very depth into the specimen, because X-rays ejected electrons, and electrons are charged particles. As you read in your graduation or post-graduation, that interaction of the charged particle with the matter. So in that process, the charged particle dissipates its energy very fast. So electrons dissipates or lose its energy in the medium. So only those electrons from the very beneath of the surface of this 10 nanometers depth are able to come out from the surface of the sample. So that's why there is no problem in the penetration of X-rays, but the problem related with the electrons that are ejected out from the surface. So deeper electrons were not able to coming out from the surface because they lose their all energies, all kinetic energy in the interaction processes, right? So this is the basic. Okay, further, the kinetic energies and binding energies of the detected electrons. The kinetic energy of an electron measured by an XPS system can determine the energy with which that electron was originally bound by its host atomic nuclei. There is an integral relation between the kinetic energy and binding energy. The detectors in the XPS actually read the kinetic energy of the ejected electrons. But anyhow, since we know that, or in the forthcoming slides, we will write a relation between the kinetic energy and the binding energy of the electrons. So the system will convert it into the binding energy of the electrons. And this binding energy by which the electrons are bound with the nucleus depends on the several factors like the atomic element. So I should here change this pen here. Okay, so the atomic element. So by meaning of the dependency of binding energy on the atomic element means that if we are taking carbon and suppose that we are talking for the 1s electron of carbon, then its binding energy is different than the binding energy of oxygen 1s. So for the different elements, their binding energies are different. Again, this binding energy also depends on the orbital previously occupied by the electron. Means suppose that we are again talking for the carbon 1s. If we are talking for the binding energies of the carbon 2p, in one case, electron was occupied in the 1s orbit. In the second case, electron was occupied in the 2p orbit. And these two have the different orbits. So they have different binding energies. So binding energy for carbon 1s is different than the binding energy for the carbon 2p. So this is what do we mean by the depends on the several factors, and that's orbital's chemical environment, that whether your carbon is surrounded by the carbon again or whether your carbon is surrounded by the oxygen, it also depends on that, or binding energy depends on that. Means the binding energy of this 1s is different than the binding energy of 1s of the same carbon in this CC bond and in the CO bond. So this is what the basic factors by which your binding energy depends, and using that same things in the reverse way, if we are able to find out the binding energy of the electrons, then we can able to find out the elemental composition of the surface of the material. Means we can able to find out that what different elements are present in my specimen on the surface, and by using those percentage, we can able to find out the empirical formula and chemical and electronic states, what different chemical states and electronic states my atoms and molecules have on the surface. So for understanding or getting the deeper insight in the surface chemistry, we have to know about the basics of the XPS. Okay, now again going through the basics X-ray generation. This is what very famous Cooley's tube, in which the cathode is here and anode is here. So in this process, cathode rays means electrons bombard continuously on anode, and by the classical electromagnetic theory, we all knows that uh, the accelerating charged particles emit electromagnetic radiations, and here that electromagnetic radiations in the form of X-rays. So these electrons deaccelerates when incident on this anode here, and in this continuous bombardment of the electrons at the anode, this anode is heated up. The electrons collides with the anode and deposit its energy in some form of heat and in some form of X-rays. So this requires cooling of this anode. Otherwise, this will burn out, and so that's why all XPS systems requires chillers, cooling systems with them. Okay, so these X-rays are the spectrum of these X-rays are here made here, and this is what Bremsstrahlung process. Bremsstrahlung means the deacceleration process of these electrons with the anode wall is known as Bremsstrahlung. So this is continuous X-rays, but further there are two horns, सींग जिसे बोलते हैं, जैसे गाय के सींग है, भैंस के सींग है, वैसे ही साइंटिस्ट ने इनको नाम क्या दिया, horn X-rays, and they are also known as characteristic X-rays. So this continuous X-rays are coming out from the deacceleration of the electrons or the cathode beam, but these horn X-rays are coming out from the anode itself. Means they are characteristics, they are properties of the anode material. They are different for the copper target, they are different for the aluminum target, and for the different materials, this characteristic X-rays are different. So we are using in the X-ray this XPS, if we are using X-ray sources, so we make these X-rays monochromatic X-rays. Okay, am I audible? Hello?
Yes.
Sir, am I audible? Yes, sir.
Yes, sir.
Actually, I am able to only see my screen. So in this online mode, after few slides, I have to take a pause and ask from you that whether I am only talking myself or with the you also. And I would like to make this presentation as simple for the very beginners and the people for starting their XPS or try to understand or analyze the XPS data. So this is again, X-ray generation is explained on the atomic energy levels. So when the incident electron ejects some inner electron, in the case from here 1s electron, so this 1s electron is known as secondary electron. So the incident electron ejected a secondary electron from the this anode material. Okay, and here is what a vacancy, and this vacancy can be filled by either the upper layer electrons. Here in this case, this electron jumps from this 2p level to 1s level, and as Bohr model says that whenever the transition from the different energy levels, there is a photon coming out. So this X-ray photon have the frequency equal to this energy delta E divided by H. So this is what the X-ray photon emitted out from here, or the X-ray generation. And these are what these X-ray photons are, characteristic X-ray photons in the previous slide. So K alpha and K beta are the characteristics of this anode material here coming out from this energy levels. Okay, so now we come to the, so in the first process we produce X-rays, and now in this slide these are the energy levels of the specimen or the sample or the material for which we are trying to extract the information from the surface. Okay, so these are the energy levels of the specimen. So we incident those X-rays coming from the X-ray source to the specimen, and there is what a process like photoelectric effect known as photoelectric process happens there on the surface of the material. And this the photoelectric effect process depends on the several factors. It depends on the Z number, means the atomic number of the material present in the atom present in the material. Also, it depends on the binding electron. So this photoelectric process is a probabilistic phenomena. In nuclear physics, we studied that this process is what completely probabilistic. Which electron coming out from which cell, either it is 1s electron or it is 2s electron, so all depends on the probability. But yes, the probability in the photoelectric effect process for the 1s electron is always more. The rule is what? More the binding electron, more the probability of photoelectric effect. So here we can see that there are certainly probabilities, different probabilities for 1s, 2s, and 2p ejected out from here. But 1s electron has the highest probability to ejected out in the photoelectric process. Okay, so these ejected electrons will analyzed by the electron detectors in the XPS, and they will give us the spectrum, and these peaks associated with the ejection of the 1s electrons known as 1s peak. Suppose that we are talking that this is what carbon in our sample surface, so this peak will be mentioned as C1s peak. Okay, so in the later or forthcoming slides we will try to see the spectrum of the XPS, and we will try to see that what do we mean by the C1s peak there. Okay, and if the electron is ejected from the 2s level, then we call it C2s peak. And you can see from here that this 2s electron is less bounded with the, here is what nucleus, and less bounded than the 1s electron. So binding energy, I can write here. Okay, so binding energy of 2s electron is less than binding energy of 1s electron. Why it is so? Because 1s electrons are more near to the nucleus than the 2s and 2p electrons. As we go far away from the nucleus, binding energies are decreasing of the orbits or electrons. So C1s peak will be on the higher binding energy side than the carbon 2s binding energy peak. And the ejected photoelectron has the kinetic energy. Like kinetic energy is what h nu is the energy of the incident photon. Binding energy is the binding energy of the electron in that particular orbit, and the phi is what work function of the material. And in the forthcoming slide, we will replace this work function of the material to the work function of spectrometer. In which way? Let us know this. And see, in this slide, we can see that by ejected electrons, what they make in this here, a vacancy in the 1s shell. So this atom now is in the excited state and have some energy with it. So this vacancy can be filled either by these upper level electrons, or this energy can directly go to these outer level electrons and the electron can be ejected here. So following this process, the atom will release energy by the emission of a photon or by a electron, and those secondary electrons are known as OZ electrons. So there are two competitive processes, either photons, emission of photons, or emission of OZ electrons. So in this slide, we are talking about those emission of OZ electrons. So when this electron fill this vacancy, or anyhow this fill this vacancy, then this extra energy will go to this electron, and this electron going to out. So our electron detector will also detect this electron, and there is also again a peak for the secondary electrons, and these peaks are not core level peaks. So this is what they are referred as the OJ peaks. Suppose that we are talking for the oxygen, okay, and if the oxygen 1s electron is ejected, and we get a oxygen 1s peak in our spectrum. Suppose that this is a spectrum, here is a peak, and we call this oxygen 1s peak. But with this process, the emission of 1s electrons, there is what the emission of this OZ electrons also there. And we know that the binding energy of these OZ electrons are smaller than the binding energy of this core electron 1s. So if this is the binding energy side, suppose that this is the reverse side, this is the binding energy side, then at the lower binding energy, there is what again peak, and that is known as OKLL. And why this is nomenclature OKLL? Because the electron is what going from L to K. So that's why these OJ peaks are nomenclature like OKLL. So whenever you are going to see your spectrum and you see that OKLL, that means that they are not core level electrons, they are OJ electrons, and they are representing the peaks in the lower binding energy than the core electrons. Okay. So again, here for the pure element, we are talking here for the pure element, that binding energy for the pure element. So the Fermi level is what fixed, right? From the nucleus to the Fermi energy is fixed, and this is what depends on the binding energy. If we are talking for the carbon, again, let us take the example of C1s. Okay. So if the electron nucleus attraction is more, if the electron nucleus attraction is more, then binding energy will be more, because this graph will come down, and this is what the total binding energy. And if there are what electron repulsion, suppose that we are calling for C2s, C2p, then they are what outer electrons, and their electron repulsion is there, and so that's why they are what less bounded by the nucleus, and they have the less binding energy. So we can say that for the binding energies, 1s electron will have the highest binding energy, for the 2s, then the 2p, and so on. So for the pure element, we can decide that the electrons or the X-ray peaks are sitting, electron peaks are sitting in this fashion. Now, chemical shift. electronegativity effect. Suppose that we are talking for the CC bond and a single bond O. For the CC bond, the electrons are what equally shared. Electrons are equally shared by the carbon in the middle of this carbon bond. Okay, but since the electronegativity of oxygen is more than the carbon, so the bond electrons are more near to the carbon, and in that sense, this carbon gets a small positive charge, and this oxygen gets a small negative charge. So now, if we want to remove a electron from this core level C1s electron, so binding energy of this, what you can say and what you can make a statement about this binding energy of C in 1s in the CO bond. Okay, so we are trying to eject electron from the CC bond in the carbon, and we are trying to eject the electron from the carbon in CO bond. So which binding energy is more? Since this time the carbon having this more plus, because due to this more electronegativity oxygen bond, so the binding energy of this C plus or this C in CO bond is more. So by analyzing this binding energy dependence on the electronegativity of the different atoms bonded with the particular atom, we can able to identify the chemical environment, that in which chemical environment our atoms are residing in the material surface. And here it is shown by a figure also. So electron oxygen atom attraction is more, or the electron nucleus attraction is more. So this is depends on the carbon binding energy. Okay, so this is XPS energy scale. Usually we express our spectrum in the binding energy side. So this side we took the kinetic energy, and this side we took the binding energy. So sometimes students or the beginners confuse in this, because what the spectrum is like this. Here is the intensity, and here is the binding energy, and binding energy are in this way, means binding energy increases in this direction. Why it is so? Because initially we are usually taking kinetic energy, and kinetic energy and binding energy are what reverse to each other. More kinetic energy means less binding energy, and more binding energy means less kinetic energy. So this binding energy scale is reverse, usually reverse in the system spectrum. So here is what binding energy and the kinetic energy of the ejected electrons are related in this fashion. The h nu is the energy of the incident photon of X-ray, by which our X-ray source uh, uh, sending the photons on the specimen of the surface of the specimen. This kinetic energy is the kinetic energy of ejected electrons, and this phi spectrometer is the work function of spectrometer. So this equation is valid for the case where the sample is metal, or better to say that they are conductive, and the sample and spectrometer are in ohmic contact. See here, if the sample and spectrometer are in ohmic contact, which causes their Fermi levels to align. So if two metals are together, then their Fermi levels are on the same horizontal level. We can see in the next slide here, sample spectrometer energy level diagram for the conducting samples. So here we can see that the Fermi energy levels of these two sample and spectrometer are aligned on the same horizontal level, means on the same energy. Okay, so the equation the Einstein gives is that what this binding energy equal to h nu plus minus kinetic energy and plus of phi, and this phi is what phi material, but we are using what phi spectrometer. Many beginners and many students are confused here. See, this is why, this is because here, because this is what the free electron energy is here, and it is fixed, right? This is fixed. So what we can write here, that this fixed energy h nu equal to binding energy, kinetic energy 1s plus binding energy and plus phi sample. And in the other equation, we can say that kinetic energy prime plus phi spectrometer and plus binding energy. So we can use this phi spectrometer with the less kinetic energy in this equation also. And suppose that our sample is not conducting. So for the conducting sample, well and good that both the Fermi levels are aligned together and on the same horizontal surface. But in the case of non-conducting samples, what is here going on, that the Fermi levels are not aligned together on a same horizontal level. The Fermi levels are on the different vertical states, different energies. And there is what the crucial role of charging effect or flood gun can be shown here. So when these electrons are ejected out from the sample, and since sample and spectrometer are on the different energy levels and they are not in the ohmic contact because the sample is non-conducting, so as the electrons are ejected out from the sample, there is what a relatively positive charge build up on the sample, and this will give us the false binding energy or the binding energy on the higher energy side. Because if the sample gets positive charge, it is more difficult to detach a electron from that sample having the positive charge than the sample neutralized sample. Okay, so in that case there is a need of flood gun. Flood gun is what, in the forthcoming slides we will discuss about the instrumentation and we'll discuss about the uses of flood gun. Flood gun is a electron gun that bombard electrons continuously on the sample to neutralize this positive charge effect for the case of non-conducting samples in the XPS measurement. Okay, students, am I audible, and are you able to hear me?
Yes, sir.
Yes.
Yes, sir.
Okay.
Yes.
Okay. Thank you. So
You can
now,
carry on, sir.
okay. Thank you very much. So now we come to we have completed the very basic and fundamental ideas of XPS, that how XPS, how, what is the role of X-rays, what are the different photoelectrons ejected, and if there is a non-conducting sample, if there is a conducting sample. Also we have discussed the requirement of chiller. Also we have discussed the requirement of the electron gun, that what is the role of electron gun. Okay, so now we come to the this instrumentation of XPS. So first, X-ray source. This is very essential to incident X-rays on the sample surface. The one here, very ultra high vacuum. Ultra high vacuum is very necessary for the various reasons. We need ultra high vacuum for the XPS system. Then the third part is electron lenses, followed by the electron analyzers, detectors, and monitors and recorders are all the integral parts of the XPS instrumentation. And here what is here is what a light source and a camera. So you can see that where your sample is actually put on this sample holder. This is a sample holder. Okay, so here is what X-ray monochromator. Here is X-ray source. X-ray source send X-rays, and here is a monochromator. Monochromator sends monochromatic X-rays, means the X-rays of the single frequency or the single wavelength falls or incident on the sample surface. Here the sample surface is here, and if the sample surface is non-conducting, then we use this flood gun to neutralize the sample surface. So this is what electron gun. Electrons are continuously bombarded on the samples at a particular rate, so that there is no buildup of the positive charges on the sample, to avoid the false values of binding energies. And here is what ion gun. What is the use of ion gun? Usually we use argon plus ion gun. The use is this, that we have already told you that this XPS can only a 1 to 10 nanometer surface sensitive technique. So sometimes if you working with the oxides, and if you working with the samples which make some contamination layer with the interaction and with the reaction with the surroundings, and those layers are thicker than 10 nanometers, then if we take directly the XPS spectrum of that sample, then this up to 10 nanometers, this is what a total contamination layer. This is not the sample surface. So in that case, we get false informations. So what should we do? We first remove this contamination layer, and this removal of the contamination layer is done by this ion gun. Okay, and here are the ejected electrons coming out this, and these are the electron lenses, and these electrons are now analyzed in this hemispherical analyzer, and here are the detectors. So their kinetic energy are measured by this different hemispherical radii of the electron taken here. So this is all about this instrumentation of XPS. Later, one by one, we will see about the uses of this flood gun. Okay, so I have already told you the use of the flood gun. So if the surface is electrically insulating, particularly insulating materials, then the emission of the electrons causes a positive charge to accumulate at the surface, and it causes the peaks. Okay, I would like to pose a question to you all. Suppose that for the insulating sample, okay, suppose that we are using this insulating sample, and a positive charge is developed on this insulating sample. Because this is insulating, electrons are ejected out by incident X-rays, so it got a positive charge. And suppose that there is a sample here, and the true binding energy of this sample is binding energy 1s. Suppose that we are taking this, okay, the same sample here. This is what binding energy true value, and this is what binding energy of the positively charged sample due to this ejection of electrons. So what you can say in the binding energy in this first case, and what you can say in the binding energy of the second case with the positive charge? Any idea from anyone, especially from the undergraduate and graduate students, from the PG and UG students? What you can comment about the binding energies of this same samples? Okay, one is having the true value, and one is what having the positive charge due to this ejection of electrons. Can anyone make any statement? No. Okay, so binding energy of this positive sample is more than the binding energy of the true value. Why it is so? Because if the sample get positive charge, it is more difficult to detach the electron further. So it will give us a enhancement or the increasing binding energy in this sense. Am I audible to all?
Yes, sir.
Okay. So you can especially from the student side, you can answer the questions, so that in the online mode we can speak into two directions. Okay, now the ion gun. Ion gun is for the removal of the contamination layer. As we have already talked that if your sample is very sensitive and it can interact with the surroundings, then it can make a contamination layer. And this contamination layer is thicker than 10 nanometers. So if we are taking this XPS of this sample, your true sample will never expose to these X-rays or to the electrons. So what you are getting is very false informations. So it's prime duty for the instrumental scientist of XPS to remove this contamination layer. So this is done by this ion gun to remove the contamination layer. Secondly, also, as we previously talked that this is very surface sensitive technique. From only 10 nanometers depth, you can get the data. So how can we get the information from the much deeper depths than beyond the 10 nanometer? So it can only be done by the use of this ion gun. So ion gun is what the energetically ions bombarded the surface of the material, and this makes the surface itched, and the each itching will shift this contamination layer. Shift to this, and this high vacuum level this sucked up and sent outside to this chamber. So by using this ion gun, we are able to go more deeper depths than 10 nanometers. We can remove the layers by layers of the sample, and this is really very helpful when we are working with the devices or the heterogeneous junctions. And if we know the exact material chemistry at the interfaces of the two layers of your device, then what we can do, we can use the ion gun, sputter this the first layer. We can reach up to this interlayer and then again sputter, and then again we can reach up to the more deeper depths where two different layers join together, and we can study that surface chemistry of the specimen there. Usually we use argon plus gun, ion gun, and these monoatomic argon ions are used in the ion gun. Okay, so what different popular sources of X-rays are using in the XPS system? They are what popularly known as this ALK alpha. These are what anode materials. We have seen in the Cooley's tube, right? In the Cooley's tube, there is what anode there. So these are the anodes, and the X-rays, the characteristic X-rays emitted out from these anodes are what ALK alpha, aluminum can be used, or the magnesium can be used, and their K alpha energies are used as the X-ray source. 1486.6 electron volt and 1256.6 electron volt. So here you can pose a question to me that, sir, if the energies of the aluminum and magnesium are only up to 1486.6 electron volt, then how can they able to eject the 1s electron of the high Z material? Is it possible? Suppose that we are talking for a material which have the very high Z material, suppose that copper. So whether is it possible from these aluminum and magnesium sources to get this copper Cu1s peak or the carbon 1s peak? Any idea about this? I would like to attract the attention of all the participants that what you can say about this copper 1s and carbon 1s. Since the binding energy of the carbon 1s is what below than this 1486.6, so we can easily see the carbon 1s peak in the spectrum. Okay, core level. But since copper has very high Z, Z equal to 29 for copper. Okay, so the Cu1s binding energy is beyond than 1486.6 electron volt. See, so for using these aluminum and magnesium K alpha sources, we are not able to see this Cu1s. You will never see this. So what you will get, the less binding energy peaks, that are what Cu2p. For in that case, you can only able to get Cu2p. So sometimes whenever we are teaching this XPS to our coursework students or to the elective students of nanotechnology, they usually ask, sir, where is Cu1s peak? Where is this Zn1s peak? So the binding energies of those high Z materials are more than the energies of the incident X-rays. So for the energy conservation process, it is not possible to eject these 1s electrons from the copper and zinc and so on. So we are not able to see this. But since we know that 2p electrons are less bounded than 1s electrons, so we can get Cu2p here. So 2p binding energy of the copper is less than this 1486 electron volt. Okay. So this is what the ultra high vacuum. So the requirement of the ultra high vacuum, since we all know that our XPS is based on the detection of the electrons kinetic energy, okay, in the hemispherical chamber. And whenever we are using electrons, dear students, please try to keep in mind that whenever we are using electrons, we have to have the high vacuum there. Why it is so? Because electron deposit its energy in the medium. So if there is no good vacuum there, then electron which is originally coming out from the particular sample have the different kinetic energy, and when this electron reach to the detector have some different kinetic energy, and that kinetic energy detected by the detector is what smaller than the kinetic energy the electron originally coming out from the sample. So it is very essential to remove adsorbed gases from the sample. And suppose that your sample may have some gases adsorbed on the surface. since surface is more reactant to the outer environment, so they will give you the false informations. So to remove that absorbed gases from the sample, we need this ultra high vacuum, eliminate adsorption of the contaminants on the sample, and prevent arcing and high voltage breakdown. Since we apply the high voltage, okay, for the XPS production and for this detection of the electrons, and if there is what the medium is there, so there is a arcing process may happen there. So prevent arcing also, we need this ultra high vacuum, and to increase the mean free path of the electrons, ions, and photons in the sample chamber, we need this ultra high vacuum. So here are what the different low vacuum, medium vacuum, high vacuum, and ultra high vacuum pressure levels are given to you for your basic understanding. So in the XPS we used we up to go to -10 and up to 10 raised to power -9 torr pressure. This is so high, ultra high vacuum. Okay, we require that, and maintaining the ultra high vacuum is very difficult. So it cannot be achieved by a single pump. Okay, so you need to the combination of the different vacuum pumps together to maintain this 10 raised to power -11 millibar vacuum level. So first we have this scroll pump, and you can say roughly previously rotary pump and scroll pumps are same, but scroll pumps are oil free pumps, so they are very safe. And they can roughly make a vacuum up to order of 10 raised to power -3 millibar. So they suck the gases from the sample chamber. Initially, they provide a rough vacuum of 10 raised to power -3 millibar. Then the role of turbomolecular pump, also known as TMP pump, starts from here, and it can take the vacuum order up to 10 raised to power -9 to 10 raised to power -10 millibar, and then the fine tuning of the vacuum level is done by this ion sputter pump, and it can reach up to 10 raised to power -10 millibar in the vacuum order. And here I wrote the different vacuum units to understand that what, because usually you use the 1 atmospheric pressure is what 10 raised to power 5 Pascal. So I wrote all the units here for your basic understanding, that what is the relation between Pascal to the Newton per meter square, and what is the relation with the atom and atmospheric pressure to the torr, because we use here millibar. Okay, here are the electron lenses and energy analyzers. So here is a hemispherical analyzer used here, and X-ray source. You can see these electrons are different energy electrons take the different paths by this magnetic shielding, and they reach up to here, and then analyzed according to their energies, and then sent to this position address converter, and then to the position sensitive detectors. And this data can be obtained in this computer system attached with the XPS system. Okay, so I am little bit going faster from here. Okay, so we have already seen the use of this electron lens, energy analyzer, detectors. Okay, so come to the data collection and the data analysis. So first, what we are going to do in the obtaining the spectrum is wide scan or survey scan, or the survey spectrum. In this, we are having a pass energy, means we are scanning from the lower energy to the higher energy, and we have a window of energies, and this window is known as pass energy. So this pass energy is more for this survey spectrum. What we are trying to find out in the survey spectrum is the what different elements are present in my sample. So that's why after getting the ideas of the different elements, I will go to the finer scans that are known as fine scans or high resolution scans. In that particular scan, this energy window or this pass energy is small, so that we can easily get the good amount of data or the good amount of intensity to analyze that particular peaks in the fine scans, and they are also known as high resolution scans. Okay, so this is the data from lab to publication, and I am thankful to the Professor Kunal Modi sir, who is our collaborator, and we do many works together. And this is what a article published in the Ceramic International, that Ca+2 substitution. Hello. Audible? Yes?
Yes, sir.
Yes.
Okay. So this is what we prepared this CCTO sample, CSU 3TI4012, and we studied this XPS spectra and try to find out that what are the different valence states of these compounds here. So I will give you some basic ideas how to analyze the data from the XPS and what kind of the spectrums visualize to us. The data analyzing softwares, we can uh, analyze the data in the origin also. Nowadays, Origin gives some background fitting softwares or background fitting functions. So nowadays, you can also, if you don't having the access of CASA or Avantage by Thermo Fisher, you can do your work, or you can start with the Origin also. There is no problem in that. Okay, and the Origin is rather more easily available to the research labs. And this CASA XPS is the dedicated software for plotting this XPS spectrum. This is a licensed version, and Avantage by Thermo Fisher. Thermo Fisher is a company who actually make this XPS systems, and they provide their own software that is known as Avantage software. So, okay, so these are the softwares to analyze the spectrums or the data get by the engineer or get by the instrumentation engineer given to you. Okay, this is the survey spectrum. Okay, so you can this is the survey spectrum of none other than that particular CCTO that in that paper. So you can see here from here to here. So this is what the scale is. What here is the binding energy in electron volt. Okay, so binding energy in the reverse scale. Usually you normally take this is the energy and this is the intensity. But here what we are using a reverse scale. Okay, for the relation with the kinetic energy. And here this x-axis is the intensity in arbitrary units. That's A dot U dot is what? Arbitrary units. Okay, so here is what you can see the C1s. So you people ask that, sir, there is no C carbon present in your sample. Then how can you get this C1s peak? Because there is what Ca2p 3 by 2 and Ca2p half peaks. Ca is present in this here. Okay, Ca2s has the here Ca2s, since you know that Ca2p is on the lower binding energy than the Ca2s here. Okay, because here is the 2s level, here is the 2p level. So ejecting the electron from the 2s level and from the 2p level, which is more easier, from the 2p level. So 2p level having the less binding energy. So this is what 2p level has having the less binding energy than the Ca2s level. Okay, so we have already studied about this in the basics and fundamentals of the XPS. The Ti 2p 3 by 2 and Ti 2p half peaks are here in the survey spectrum. So okay, the answer of this carbon is what this peak is also known as advantageous carbon peak or the contamination carbon peak. Your sample is exposed to the surroundings or to the ambient environment. So in that case, some carbon is deposited on the surface itself, and luckily we use this carbon peak for the calibration purpose also. So that's why this is, even though this is what a contamination peak, but we use this for the calibration. So sometimes we also refer this peak as advantageous carbon peak. Okay, and here is what Ti2p 3 by 2, and here is what O1s, oxygen 1s peak is here, and CuLmm, and CuLmm. Okay, three different peaks. And what are they? They are OJ peaks. Okay, we have already studied that OJ electrons are the competitive process with the core electrons. So the Cu2p peaks are here. This is what Cu2p3, and this is what Cu2p half peaks. And we have already discussed also that OJ peaks have the less binding energy than the core level electrons. So the 2p electrons are here, binding energy, and the OJ peaks are here in the less binding energy side. Okay. So this is all, this is oxygen KLL, OJ peak of oxygen. Okay. So coming to the next slide, these are what the fine scans. So now we got the idea that the what different elements are present in my sample. Then I go to those particular energies and then having a very smaller pass energy and scan those particular elements. So this is what carbon 1s peak. Okay, so the carbon 1s peak. So there are, what you can see, that there are in survey spectrum, what you can observe, that sometimes there are doublets. Sometimes you see that there is Ca2p doublet, Ca2p 3/2 as well as Ca2p half. Doublets are here. But sometimes you are only getting C1 as single peak. Here again, you are getting oxygen 1 as single peak. Why it is so? Sometimes the doublets, sometimes singlets, because it depends on the spin orbit interaction. L stands for the spin orbital momentum and S stands for the spin angular momentum. So this LS coupling or the fine structure is responsible for the single peak or double peak. Since we know that for 1s electrons, what is the L value? What is the L value for the 1s electron? 0. Okay. And what is the S value for the electron? Is half. So what is the J value? Only single J value, because J can take L minus S to L plus S values. This J is what? Total angular momentum. Okay. So for the S electrons, we will always get a single peak. Whether it is from the carbon, where it is from the oxygen, we will get only the single peak, because there is no splitting due to the spin orbital coupling for the S electrons. And here you can see that this 1s peak of the carbon shows some asymmetric nature, and this asymmetric nature reflects that there are different chemical environments in this carbon. The first is the lower energy binding energy side is what? CC bond. The second hump is there. You can fit a particular peak in there, and this is responsible for C single bond O. Here a separate peak you can see, and you can fit here a separate peak here. You can fit a peak here, and you can fit a peak here. This peak will refer to the CC bond. This peak will refer to the C single bond O. This peak will refer to the C double bond O. So we know that in the C double bond O, this carbon get a more positive side. So the electron, so the ejecting the electrons from this carbon to this carbon and to this carbon are different. So the binding energies of this 1s is more than binding energies of this 1s, than binding energies of this 1s, because carbon having the different chemical environment surrounding to those carbon atoms. Sometimes it makes double bond O. So that's why what we have said in the previously, that we can able to identify the different chemical species in which our material is sitting there. So we can identify that how many carbons are there attached with the single bonds, how many carbons in percentage with the single bond O, and how many carbon are there with the double bond O. So this gives you the precise idea that what are the different percentage of your specimen sitting with the what chemical environment. Here Cu2p peaks. Okay, so Cu peaks almost at the 950 electron volt energy, and you can see there is a crystal clear doublet, Cu2p half and Cu2p 3/2, and you can see that Cu2p half is on the more higher binding energy side. This is binding energy, and 2p is at the higher binding energy. Why it is so? Because in this way, LS coupling, L is what for the p orbit, L is what? 1. For the electron, S is half. So this time 1 minus half, J can take values from 1 minus half to 1 plus half. So this is what? Half, and this is what? 3/2. So your total angular momentum can take two different values, either half or 3/2. So these peak corresponding to the J 3/2, this peak corresponding to the J 2p half. Okay, now see that from the energy perspective, how these peaks or how these energy states are arranged. So this is what your P half, and this is what P 3/2. Okay, so in this is what your energy. So the P 3/2 is situated on the more higher binding, more higher energy side than the P half. So it is more easy to detach an electron from here than here, because you need more energy to detach this p half electron. So in other words, you can say that the binding energy of the Cu 2p half is higher than the binding energy of this Cu 2p 3 by 2. So that's why these 2p half peaks are on the higher binding energy side. And there is a gap of 19.75 electron volts between these two p peaks of Cu carbon. And this is what the characteristics of the copper. If you are getting two peaks, they are separated by the 19.7 electron volts. So you can say that, okay, these are the copper peaks if the peaks are found around 950 electron volt. Okay, so by this way we can able to find out the different elements, their species, and so on. And this is what Ti2p again. So in this case, in the survey spectrum, you have not seen Cu1s. Okay, as we already talked about it. Again, here you got Ti2p. In the same sense, Ti2p 3 by 2 and Ti2p half. Ti2p half is on the higher binding energy side, and this is characteristic is what these are the oxides, and the separation between titanium oxide peaks is what 5.7 electron volts. And this is what oxygen. Since oxygen 1s electron, we are talking about oxygen 1s electron, and for this s orbit L is 0, so there is no splitting. Spin orbit splitting is not there in the oxygen 1s, so only a single peak of the oxygen is there. And the different, here are the different peaks for the different samples. I changed the concentration in the Ca+2 in my sample, and the different samples were prepared. So these are different oxygen peaks for some different samples. Okay, now in this slide, this oxygen slide, I can tell you that how we can fit the data. By using this origin software, or by using this CASA software, we can able to identify that what are the percentage or what are the ratios in which our oxygen is lying in this. Okay, so we fit this oxygen, and clearly you people are able to see that there are three different peaks. One peak is here, crystal clear peak is here. Second is this hump is here, and the third, again, this asymmetric nature tells us that a higher binding energy side there must be a peak is here. So these three peaks are nomenclatured as P1 peak, P2 peak, and P3 peak. So this P1 peak, which is on the lower energy side, this is ascribed to the lattice oxygen. Means the oxygen which is sitting there with the lattice, means CCTO. So this is what oxygen is, lattice oxygen. So this peak P1 at the lower energy side tells us that the oxygen that is what having the bonds with the this Ca calcium and this titanium and this copper. This P2 peak is oxygen defects, and this P3 peaks is the absorbed or chemisorbed oxygen. Sometimes the some humidity in the environment, and these humid water droplets are consumed or on this surface of the material. So these oxygens are here as absorbed oxygens, P3 peaks. So we can identify that what are the different species of the oxygen present in my sample. Okay. And this oxygen peak is found around this 531 or 530.5 electron volt. So in the conclusion, we can say that XPS is a technique for analyzing the surface chemistry of a material, and XPS can measure the elemental composition, the empirical formula of the material, the chemical and electronic state of the elements present within the sample, and the XPS spectra are obtained by irradiating a solid surface with a beam of X-rays while simultaneously measuring the kinetic energy and thus binding energy of the electrons from the top of the 1 to 10 nanometer layer of the sample. So in conclusion, a photoelectron spectrum is recorded by the counting ejected electrons over a range of electron kinetic energy. Peaks appear in the spectrum from atoms emitted electrons of a particular characteristic energy. So these different peaks, so see, here I would like to take a pause. Nature gives us different elements. Nature gives us different atoms. Nature gives us very different electrons, very different binding energies. But these binding energies are not same. They all are different, which C1s binding energy is not same as the oxygen 1s binding energy, and not same as the Cu2p binding energy. So whenever nature creates some challenge to us, it also facilitates us by having some solutions to us. So in this way, XPS, we can say that the different peaks are the characteristics of the different elements, and the energies and intensities of the photoelectron peaks enable us to identify and quantify of all the surface elements. And these two low Z elements are very difficult to identify, so we are not able to identify this hydrogen and helium from these XPS. And I'm very happy to share that we at the Department of Physics, University of Rajasthan, have this thermofisher Nexa G2 surface analysis system, XPS system, and we are very open for the collaborations. If any researcher trying to solve the mysteries of the surface material, surface chemistry of their samples, we are very ready and we are very open for that collaborations. So these are the useful links, different links from which we can study the thermofisher XPS. Okay, I'm just going to wind up my presentation. Okay, no problem. Okay, I'm in the last of my slide. So this thermofisher XPS website is very relevant website. This is previously also known as xpssimplified.com website. So the beginners can use this website to know the different species, the different chemical states, what is the proper binding energy of your element, and how can the fitting can be done in this specimen, and so on. And these are some yellow books are also published by CASA XPS. They are also helpful for understanding the this XPS. And you can also use this Phi handbook of X-ray photoelectron spectroscopy. So these are the links here. And in the acknowledgement, I would like to first and foremost my sincere thanks to my guru as well as my mentor, Professor R.K. Singhal sir, who actually guide me throughout my PhD also, and who taught me the each and every fundamental aspect of XPS. So I'm really very thankful to him. And today I presented the lecture on XPS. I pay my gratitude to him. He is currently head of the department at my department, University of Rajasthan, Jaipur, and my whole research group working at University of Rajasthan. So thank you very much. It is from my side. So if you have any queries, I'm very happy to answer all the queries of the students. So that's it from my side. And thank you very much for your patience.
Hello, Dr. Narendra, you finished?
Yeah.
So on behalf of organizing committee, I am very much thankful for delivering a nice talk by Dr. Narendra Jakhar on XPS and allied concept with some typical examples. So now the session is open for the audience. If they have any queries or questions related to this XPS study. Session is open for the question.
Sir, there are questions in chat box.
Okay.
It may be in chat box.
Yeah. Actually, at the time I was on the presentation, so could not able to see this chat box. Okay. No. You cannot able to find out the film thickness using XPS. Chintan, you cannot able to find out the film thickness using the XPS. You can go for the different methods other than XPS to use this. What from the XPS we can sputter your thickness of the film. Yes, we can go up to the deeper depths. Yes, Chintan, you can speak out.
Yes, sir. So what I'm asking is, somewhere I had read by different modeling and by fittings, we can do that. So I had that doubt. Is it possible or not?
No. Not by XPS. Not the precise value of XPS. Not the precise value of XPS. Okay.
Okay. Thank you, sir.
And okay, which element was the effect not possible? Was the effect not possible? Actually, I don't have a clear-cut answer about this. In which element was the effect is not possible? Sorry. Okay, and more questions. Okay. And you can write your questions here in this chat box. Yes. Tushar Bhatt. Yes, there is certainly some different, many difference actually, many difference between the EDS. EDS is for the energy dispersive spectroscopy. Okay, usually it is done in the done with the TAM and SEM. Because in TAM and SEM, what you are using that what you are using is electrons. Okay, so that electrons also eject some electrons, and these photons are coming out from the elements or from the sample surface. So those are analyzed by the detectors, and this is known as EDS. So it will provide us the elemental information, but it will not provide us the chemical states of the elements present in the sample. But XPS can also provide us the definite chemical states and the electronic structures also. No. Indu, AR Indu, no, we are not able to find the atomic positions from this. So we can confuse with the OZ electron peaks with the element peak. How we will illustrate that is the peak from OZ electron. Okay. See, Karuna, the OZ peaks are different than the elemental peaks. Okay, how they are different? That when X-ray falls on your atom or falls on your element, the core level electrons are ejected out. As I have already told that the photoelectric effect is a probabilistic phenomena in nuclear physics. So the more the bound electron is there, the more probability of getting it out or ejected with the photoelectric process. So whenever these electrons are coming out directly by the virtue of the interaction of X-rays with the electrons, and the electrons are ejected out, this is known as core level electrons or the elemental peaks. Okay, but OZ peaks are coming from the secondary electrons. Whenever these vacancies, by ejecting those electrons filled by the upper level electrons, sometimes there are emission of photons and sometimes there is no emission of photons. This is anyhow, I don't know what is the process, and this is very open question still, that what is the process of giving this excited energy to the electron, outer electrons, and in this process again a secondary electron is ejected. So these secondary electrons are OZ electrons, and since we know that this core level is below, so core level is below, so this is having the high binding energy, and they are not peaks. OZ peaks are actually more not sharp as the elemental peaks. Okay. In the spectra, how we will know that? Karuna, okay, in the spectrum, see, the spectrum is what calibrated with the help of carbon 1s. And since nowadays we are what, okay, I'm just going to stop this presentation. Okay, nowadays what we are having this flood gun with us, and there is no much variation. There is no much variation in the binding energy of the elemental peaks. So this carbon 1s peak is used by us. So in the survey spectrum, whenever you receive the data from the XPS instrumentation scientist, he will give you the idea that this is your C1s peak. So you can recalibrate your spectrum with the C1s peak, that is for the 284.6 or 284.8 electron volts. So now the calibration should done with the help of this carbon 1s advantageous peak. That is what C1s 284.6. Okay, so by that you can able to know the different binding energies of the different peaks, because the binding energy of the peaks are fixed. So you can just refer the Phi book, or you can just refer the XPS simplified website, that what are the binding energies of copper, then you will get the idea that this is around the 950. So you can get, if you are getting that peaks of the 950, then you are certain that I have already calibrated the carbon with the spectrum, so these 950 peaks can be assigned to the copper 2p. Okay, So this is the way to calibrate your spectrum and know the different peaks or OJ peaks. Bhavesh, sir, all bonds such as CC, C double bond C and C have unique energy values irrespective of their compound. Can we use it in the tandem with IR spectroscopy for chemical bond elucidation? Okay, Bhavesh, yes, they have. See, we are not here calculating the bond energies. Okay, we are not calculating the bond energies. C bond energy, C double bond C, and C single bond C. What we are trying to do is we are trying to analyze the binding energies of the electrons of the carbons or oxygen. If the carbon is making a single bond of C, then the binding energy is different. If the carbon is making C double bond O or the C single bond O, then the binding energy is different, because this time carbon is associated with the with the oxygen, and oxygen is what is more electronegative than the carbon. So the bond electrons are more tending towards the oxygen. So a carbon will get a positive charge. So now the ejection of the electrons from this positive carbon is very difficult, or more difficult than previous one CC. So this is these binding energies are high on the higher side. In the IR, what you are using is the vibrational modes or the functional modes. So they are not in that same category. Here we are using this elemental analysis, as well as we are finding out the electronic environment, chemical states. Okay. So I'm very happy to get the questions from the students. If these are the questions, then I'm really happy that I'm able to get to the students, because I mainly targeted them so that they can know that yes, there is no difficult task to analyze this XPS spectrum. This is what just 11th and 12th level your orbital theory, by which you can just say that what is the binding energy of 1s, what is the binding energy of 2s and 2p, and what is the binding energy of C single bond C, and what is the binding energy of the C double bond O, and that's on and so on.
So you finished, sir?
Yeah. I have already finished.
Yeah. Again, I'm very much thankful for giving proper answer to our students. So thank you, sir.
Thank you very much for providing this nice opportunity. Thank you, Devraj sir. Today only I talked to him. Thank you very much. And all the organizers,
Okay.
I would like
Very
to
soon
extend
we
my
are going
heartiest
to,
thanks.
yes. Okay.
Sir, namaskar, Devraj ji.
Namaskar, sir.
Pranam, sir. Pranam, sir. What a fortunate coincidence, sir. Whatever we think in our mind, we will surely get that. I especially I thank you in the just 2 or 3 hours back, and I got you in the skin. Thank you very much, sir. Namaskar, sir. Namaskar.
Okay. Hello.
Okay, sir.
Very soon we are going to start our next talk. Dr. Archana is joined. Hello, Dr. Archana.
Yeah, I'm here.
Okay, then no problem. So can we start the next talk, students, or anybody wants 5 to 10 minutes break? Without break we can continue, no? So that in time we can complete it.
Yes, sir, we can start.
Then I would like to introduce Dr. Archana Lakhani. So her BSc and MSc, that is both from Vikram University, Ujjain. She is BSc gold medalist. She completed her PhD in 2005 in experimental condensed matter physics from UGC DAE CSR Indore itself. Then she spent 1 year as postdoctoral fellow at Institute for Plasma Research, Gandhinagar, Gujarat. She also spent 1 year as cryogenic scientist in ultra low temperature division at Oxford, UK. And since 2007, she is scientist G at UGC CSR Indore Center. Her research interest is related to study of physical properties at low temperature and high magnetic fields, functional magnetic materials, quantum materials, topological materials, strongly correlated electron systems, chiral intermetallic alloys and Huxley alloys. She received one award also, that is MP Young Scientist Award in 2006. She published more than 120 research papers. So, out of these 120 papers, we have one joint publication in JALCOM. Do you remember, Dr. Archana? We
Yes, sir.
have one joint publication
Yes.
that is published in JALCOM.
Yes,
So
yes. I do remember, and some measurements were done in my lab from that paper.
Right. My student Hiral worked there.
Yeah, he did.
In addition to several research paper presentation at various national and international forums, in her credit also. So today's talk title, that is Introduction to Quantum Materials at Interface of Physics and Technology, a magnetotransport study. So she will talk on this title related on this title. So please, Dr. Archana Lakhani, you can start your talk.
Sure. Is my screen visible to everybody?
Yes, I can see it very clearly.
Yes, ma'am. Can you please make it full screen, if possible?
It's already full screen.
We can see we cannot see the full screen presentation mode.
Okay. Yeah. Is it visible now?
Yes, ma'am, but not in the slideshow mode.
Oh, still.
If you can share the entire screen, then it will be possible.
On my screen, it is fully shared. How about now?
Same, ma'am. Ma'am, if you can share, stop sharing and then share the entire
I
screen.
did twice this thing.
Okay.
Okay, I'll do it once again.
Share the entire screen.
Respected ma'am, there is an option to share window or entire screen. So
Yes.
if you can choose the entire screen, then it is possible. Thank you, ma'am.
Is it visible now?
Yes. Perfect, ma'am. Thank you, ma'am.
Thank you very much. Thank you very much, Professor Jayant, for such a nice introduction and letting audience know that we are collaborators already. And I would
Welcome.
like to thank patrons and organizers as well for organizing such a nice, beautiful and big event. I'm especially thankful to Professor Nikesh Shah and Professor Piyush Solanki for giving me this opportunity to speak on this big science event. Professor Piyush is a longtime friend and collaborator. Thank you, Piyush. I would like to thank Professor Vivek Pai as well as Professor Atul Gonsai also for the nice words. And as Dr. Gonsai said, how science is creating wonders in our daily life. He gave some examples about how information technology has been progressing since long from our country, and how we have been progressing in this particular area. I'm sure you would see some experimental and practical glimpses in my talk about this. In this talk, whatever I'll be presenting is work from my laboratory, specifically on transport measurements. And I would like to thank my students for this. I would be showing some of their slides also, some of their data. And faculty, one of my long-time collaborator, Dr. Devendra Kumar, of course, my guide and faculties at CSR. So this is the institute where we reside. This is UGCDA Consortium for Scientific Research. This is a small building which you see, and the garden here, the gate. You see it's quite a small building, but it resides inside this huge DAVV campus. Although the building looks small and old from outside, but the facilities inside this are very fascinating and mega facilities, and really a cluster of all the characterization facilities at one center. So we have many magnetic measurement facilities, transport and thermal measurement facilities. We have scattering techniques for all the characterizations of the samples. We have spectroscopic techniques. We have thin film deposition facilities. We have facilities for making polycrystals and single crystal samples. And specifically, we have good microscopic techniques also, like TEM, SEM, and SPM, in which we have this AFM and MFM modes as well. And these facilities, I'm very proud to say that we have these at low temperature and high magnetic fields also, because doing magnetic measurements and transport and thermal measurements at low temperatures are very important for understanding the basic phenomena, as well as to understand how they will be working, how they are applicable in technologies is also important first to understand at low temperatures. So when we have this basic understanding, then only it can be incorporated in the applications. So this is one photograph of, we have this huge sample preparation facilities also, which includes this sealing facility and number of furnaces. He's my student who's working on this system. We have X-ray diffraction and HRXRD also. And this is one of the facility for seeing the topography of the sample, which is called atomic force microscopy. We have these two different microscopes, we both are working. We have this, this is an example just to show that how the topography can be seen with the help of AFM. We have this this is a gold ruling image, which shows that 5 micron by 5 micron image, and we can see this, each square is 1 micron by 1 micron size. This is possible to see with the atomic force microscopy. This is an image of platinum coated grid, which also shows the 1 micron by 1 micron grids. This is another image of mica, which can resolve even up to the atomic level, and we can see these projections are actually the atomic projections. These are atoms. And if you see the size of this, is total size of this whole picture is 5 nanometer by 5. It's taken at 5 nanometer by 5 nanometer size. This is one of the facility which I am heading. This is 9 Tesla ppms system, and it can go down to 2 Kelvin, and on the higher side of temperature can go down to 400, go up to 400 Kelvin, and the magnetic field, maximum magnetic field, can be measured up to 9 Tesla. We do resistivity and Hall measurements in this system. If anybody is interested in doing these measurements, they can write to me, or they can directly go to the user portal and send the request. We have another facility of which I said, as we have many magnetometers. One of them is 14 Tesla vibrating magnetometer. We have the 7 Tesla squid magnetometer and 7 Tesla squid VSM also for high resolution magnetization measurements, as well as for the fast magnetization measurements. We can do all these things because low temperature measurements and high magnetic fields, because we have a very good cryogenic facility. So We have this liquid helium plant in which we liquefy the helium gas, which can be liquefied 20 liters per hour if we have pre-cooling the system already. We also have this liquid nitrogen plant in which we liquefy the nitrogen gas. This is all in-house, and this is our cryogenic facility. We also have a dilution refrigerator in which we can go down to millikelvins. This is the only known method for continuous refrigeration, which works on the principle of quantum mechanical mixing of two isotopes of helium, helium-3 and helium-4. I'm showing this picture of old dilution refrigerator, although we have one newer and sophisticated dilution refrigerator in which we can go down to 100 millikelvins. This is the older system on which I worked for my PhD. It is quite a complicated system and has many different parts which are utilized to go step by step to lower temperatures. The lowest temperature we achieve is in this mixing chamber, which consists of this either copper or brass, and down to this is sample holder. In this mixing chamber, only the phase separation of helium-3 and helium-4 occurs, which is the principle behind this system. I just wanted to show you, give you the glimpse of some of the facilities which are unique to this particular institute, which you people, from many universities and institute already utilize, and you can utilize for these measurements. So what we do temperature experiments at low temperatures. So before I start telling you how, what temperatures I'm talking about, at what temperatures we do, I would like to give you a scale, an introduction to the temperature scale. Like you all know that the center of sun is very hot. Its temperature is around 10 to the power 8 Kelvin, and the surface of the sun is around 10 to the power 4 Kelvin. And we all reside at around 300 Kelvin. We call temperatures as 27 degrees Celsius, 25 degrees Celsius. If we convert that into the Kelvin scale, it comes around 300 Kelvin, 27 plus 273. So we talk about organic life at 300 Kelvin. And what scales I'm talking about where we do these measurements are below this 300 Kelvin. When we say liquid nitrogen, that is the boiling point of liquid nitrogen is 77 Kelvin. Boiling point of liquid air is 80 Kelvin. Boiling point of liquid helium is about 4.2 Kelvin. Superfluidity in helium occurs at about 2.17 Kelvin. And helium-3, the other isotopes have boiling point even smaller. So we can go, when I'm talking about temperatures 2 Kelvin and millikelvin, we are talking about temperatures below the helium boiling point of helium. So this is the temperature scale where we work and we try to understand the properties of materials. So why do we want to go at such low temperatures? Because the low temperature in low temperature physics is really very interesting. The matter behaves very differently at low temperature, and the properties of these matters actually drastically change, especially the thermal, electrical, and magnetic properties of many substances undergo various great changes. The famous example is superconductivity. So if you see, there is no resistance below a certain critical temperature. That is what in superconductors happen. In superfluidity, the liquid helium can flow through without any viscosity. So in this talk, I would like to introduce you with some of the basic properties, which are transport properties and magnetotransport properties called resistivity, magnetoresistance, and Hall effect. And then I would give you some examples of interesting functional and smart materials, which are superconductors, shape memory alloys, and topological insulators. Especially nowadays, these quantum materials called topological insulators are talked a lot, and they have really good applications in coming days. So I'll be introducing to some of these talks for the researchers. And some of the research work which we do in recently we work on topological insulators. So I'll be showing you some of the results on these quantum materials as well. So for the students, for the sake of students, because as I heard that in this Vigyan Yatra, we have many BSc students with us, MSc students, research scholars, and faculty members. And I hope everyone would have some takeaway message from this talk. So I start with a very basic property called resistivity. This is the property of material that opposes the flow of charge. So if you see, we have this circuit in which this is an incomplete circuit. Yeah, there was some noise in between. Okay, so we have this incomplete circuit. If I complete this circuit by a gold foil, that means if I put a very conducting material, we see that this shines bright. If I put a glass slab on in between, we see it doesn't shine. That means the circuit is not complete. We can make out from this that gold is conducting, whereas this glass slab is not conducting. So resistivity of gold is minimum. That means it is highly conducting. And if we have something in between, which is called silicon or germanium, if you see the light, the bulb glows not with that intensity as it was with gold. So resistivity of gold is minimum, whereas for silicon lies somewhere in between gold and this glass. So electrical resistivity is actually an intrinsic property which quantifies how strongly a material can oppose the flow of current. So a low resistivity indicates a material that readily allows the movement of electrons, which depends on actually on these parameters. And we can measure this by directly measuring the resistance based on Ohm's law. If we apply the current along this sample and measure the voltage along the two leads in between, we can find out from the resistance, voltage and current, we can measure the resistance. But the intrinsic resistivity depends upon these parameters on number of electrons, type of charge carriers, how scattering is happening. So it varies from material to material. And resistivity in general depends on structure and temperature as well. So how the atoms are arranged, what are the extrinsic parameters, temperature as well as magnetic field. It depends on those parameters also. And when we say that we do measurements at very high magnetic fields, what kind of magnetic field scales we are talking? This is explained in this particular slide. We call that we do magnetic field up to 9 Tesla, 16 Tesla. But I would like to tell you that the magnetic field which you can see inside this toaster, that is just few milligauss. And if you see in this loudspeaker magnet, that is also some 10 to 20 kilogauss. But we are talking here the magnetic fields which can be generated with the help of superconducting wires. With these magnets are made up of superconducting wires, and they with the help of these we can generate this 9 Tesla and more than that by using niobium titanium wires, niobium 310 wires, and as well as even we can go even to higher magnetic fields by using these hybrid magnets. So what is magnetoresistance? When we combine this resistance with magnetic field, when we measure the change of resistance with magnetic field, that is called magnetoresistance. And this resistance can depend either on magnetization of the material as well as on the magnetic field, external magnetic field applied on this. So magnetoresistance is given by the change in magnetoresistance in field as well as without field, and this ratio provides us the magnetoresistance. And if we multiply with 100, we call the magnetoresistance percentage, which we usually talk about in our measurements. So the experimental observation for ordinary magnetoresistance is that resistance is changes quadratically for small fields as well as but linearly at high fields. And this is the experimental observation. And why it changes? Because electrons orbit around the field until they are scattered. In presence of magnetic field, we have longer relaxation time as well as the deflection of charges gives rise to higher resistance. There are various types of magnetoresistance, ordinary magnetoresistance, anisotropic magnetoresistance, giant magnetoresistance, tunnel magnetoresistance, colossal magnetoresistance. And nowadays people talk about extremely large magnetoresistance, which are useful materials in technology a lot. So in case of ordinary magnetoresistance, when it is just applied, in case of ordinary metals, we get only few very small change in magnetoresistance. When we talk about anisotropic magnetoresistance, it depends on band structure and scattering. It is directional dependent. Applying along this different axis of the crystals, the magnetoresistance could be different. In giant magnetoresistance, it actually depends on spin. It is a spin dependent transmission and scattering. So it was first discovered by Ford and Gunsberg, who got Nobel Prize in 2007. And we talk about colossal magnetoresistance in manganites. This is because of coupling between charge and magnetic ordering. And we will see in detail what extremely large magnetoresistance is. So giant magnetoresistance is, as I said, it was Nobel Prize was given in 2007 to these two gentlemen. And this giant magnetoresistance led to various applications in read heads of hard drives, GMR sensors, and magnetic memories. And typically, the magnitude of giant magnetoresistance is order of 10 or 200 at low temperatures and in few Tesla magnetic fields. Whereas extremely large magnetoresistance is of the order of 10 to the power 3% and more. That means the magnetoresistance in field in comparison to zero field changes 1,000 times and more. And you will see in this lecture that it could, in many materials, it can go to beyond 1 lakh percentage also. So in metals, we see that the scattering, when we apply the magnetic field, it changes, the electrons change path, the orbit, they revolve around in these orbitals, and due to the deflection of these charges, the resistance changes and we get this kind of charge. Even electrons get deflected by these defects present in this sample. In semi-metals, we have electrons as well as holes also. So the MR is given by this equation. And this MR is usually the high MR, this such a large, extremely large magnetoresistance is supposed to be because of the compensation present in the material, very high mobilities. And it is said nowadays in terms of quantum materials, we call them, they have non-trivial band topology, which also causes to have extremely large magnetoresistance in these materials. So we see almost 10 to the power 5 to 10 to the power 6 times percentage change in these materials. It is seen in many rare earth pnictides and Dirac and Weil semimetals. And most of the metals, are non-magnetic materials, and they have very complex electronic structure. And due to compensation of charge carriers, ultra-high mobility, and non-trivial band topology, the XMR is caused and is a very useful property from application point of view, which can enhance the speed and storage capacity of the computers. This is one of the example of extremely large magnetoresistance done in our on antimony, which was done in our laboratory. I'll be telling you in detail if time is there. So from the simple resistivity measurement, what we can get, what can be studied. So from physics wise, we can get the information about the effect on transport properties due to defects and disorder. We can even understand the effect of short and long range ordering. We can understand phase transitions and phase transition based transformation kinetics, critical transformation based on composition and temperatures. And from practical point of view, it can be, this is a property, a simple resistivity is utilized in almost all electronic devices, in temperature measurements and in signal and power transmissions, precise resistance measurements in switching devices, and understanding the specification of purity also. Because the resistance in the quantum Hall resistance, which is perfect up to 12 digits also, if we can find out E square by H, it is utilized in the, to understand the purity of the materials also. So next property which I want to discuss here is the discovery of the Hall effect. Hall effect. It was first discovered by in 1879 and by Edward Hall, who was a graduate student at Johns Hopkins University in Baltimore. And this effect was discovered 18 years before the discovery of even electrons. So Hall effect is simply a Hall voltage, or we can say Hall effect is something which our Hall voltage is something which arises with the flow of electron through a conducting material when it is exposed to magnetic field, when it is generated across the current path. That means we know what we measured the magnetoresistance. We get the magnetoresistance when we measure the voltage along the current path, whereas we get the Hall voltage when we measure this particular voltage across the current path. And both this Hall voltage is proportional to current as well as the applied magnetic field. And this is a very important observation in material science, because it is a very important diagnostic tool from the characterization point of view, for especially for semiconductors. So what it is, I would like to explain in a few slides. What Hall effect is for students. Although you must have read this in your MSc and BSc classes. So with when we have a metallic rod or semiconducting rod of rectangular cross section, and we try to apply an external electric field along the x-axis, electrons would flow in the opposite direction of the electric field when the field is absent, when there is no magnetic field in this. But when we switch on the magnetic field perpendicular to this electric field, the electrons will experience the Lorentz force and will deflect towards the end of this rod, towards the sides of the rod in the y direction, and will form these surface charges. And after some time, due to charges on the surface, a transverse electric field called Hall field is developed on the rod. And due to this electric field, the compensation occurs, which is the compensating drift of electrons, which starts in the positive y direction, in the opposite direction actually. So we actually get, when we measure this voltage across the current path, we would get this Hall voltage here. So if we can measure this Hall voltage, from this Hall effect, we can find out the type of charge carriers, whether they are electrons or holes. We can find out the mobility of charge carrier, that means how fast these charge carriers move inside the sample, and the concentration of charge carriers, the amount of the concentration, the number of charge carriers, charge density. And conversely, if we know all these parameters of a material, what kind of charge carriers are there, with what mobility they are moving, and how many number of charges are there, we can find out exactly the external magnetic field which is there around this particular, that is what is used in case of Hall sensors. So these Hall sensors are used in various electronic devices, like in cellular phones, computers, digital cameras, navigation systems, and electronic toys, and more. So I would not explain all these things in details, but these are some pictures to create interest among the students, how in portable electronic devices, in this integrated circuit electronics, how these Hall sensors are used in day-to-day life. So all of you have these mobile sets with you. At every point, even if are moving and sliding, these Hall sensors are used in these devices. So in semiconductor technology, these Hall sensors are really used very effectively. So Hall sensors provides an effective alternate to chemical switches also. And these are used in screen orientation also. Like in these applications, it is necessary to use Hall effect sensor that is not only capable of detecting the magnetic field only, but also discriminating between the field polarities. So these north pole magnet and south pole magnets, with the help of these kind of Hall sensors at various places, the screen orientation can be done. It is possible to use Hall sensors with the human interface also, where these jog wheels or track balls are required, which move up and down and right and left in case of mobiles and various electronic devices. It is also, Hall effect is also used in car rotating sensing, especially one of the effective use of this is Hall effect sensors are used in speed measuring sensors in cars and in other rotating systems. And what happens is these Hall effect sensors measure magnetic field, and they are usually attached to the magnet is attached to one shaft and the sensor to the another near the moving magnet. the sensor produces a pulse, and each time the magnet comes near to this shaft, once every rotation to the shaft, and that's how the speed of the cars is measured. I mean, any rotating device, I mean. And this is possible. Hall effects are used in the laboratory also. We had this scanning hall probe microscopy, which is a technique for imaging localized surface magnetic field quantitatively. So in this case, what happens is we have this, we can have these Hall sensors and scan over the surface to understand the or to visualize the topography of the sample. So in this particular instrument, a micron size Hall probe is scanned over the surface of the sample to measure the perpendicular component of the field, and STM technique is used to position the sensor. With the STM technique, the sensor is positioned and then it is scanned over the surface. So that's how the apart from this AFM technique, this is also one powerful technique with which if we scan the Hall sensor, we can even find out um, uh, the local magnetization of the sample also, which gives a magnetic image also. And you see this particular slide shows the imaging at the microscopic level for a hard disk. And this is one sample in which we had done these at different temperatures, which shows that at 150 Kelvin, it has totally a different orientation. Suppose it is antiferromagnetic, and this black shows the ferromagnetic at low temperature. If you see, the black spots are enhancing this. These pictures are this particular picture is the I mean topographic picture of one hard disk, and you see these long kind of patterns. These are the bits in this, and these are about 40 micron size scanned image. If you lower this to 20 micron size, we see only few bits, and this is one bit. In hard disk, the information is stored in the form of bits, which you can see clearly in this scanning hole microscope image. So now coming to this was about some techniques which we do in our laboratory, which the magnetotransport techniques, basically resistivity, magnetoresistance, and Hall measurements. Now I would like to tell you, briefly introduce you to some interesting materials which we work with at low temperature and high magnetic fields. So one example is superconductors. I would like to give three examples if time permits. Superconductors, shape memory alloys or Husserl alloys, and topological materials, which are actually quantum materials. So in superconductors, we all know under normal conditions, to get an electric current to flow through a wire, you need to apply a finite voltage difference between the two ends of the wire. And as I said, we measure the electrical resistance with the help of this Ohm's law. So electrical resistance is analogous to the friction or viscosity, and because of this resistance, electrical energy is converted to heat in the wire, and that is the drawback. So if we have superconducting materials, we will have this uh, this heat will not be there, and resistance can flow through with a very and because if resistance will be zero, the resistance current can flow through continuously without any hindrance or friction, and that would be very useful for many of the applications. So this is a special situation where electric current flows without resistance, and these are the materials called superconductors, which was first discovered in 1911 by Kamerlingh-Onnes. So Kamerlingh-Onnes won the Nobel Prize in 1913 for this discovery, and he one of the famous experiment of him is in 1914 he started flowing a supercurrent in a lead wire, and after a year he found that it was still flowing with no noticeable change. And this became possible because of the liquefaction of helium. He was a scientist who even liquefied the helium in 1908, and in 1911 he discovered superconductivity in mercury wire. And coincidentally, the boiling point of helium and the superconductivity of mercury happens at same temperature, that is 4.2 Kelvin. And the quantum origin, why this superconductivity occurs, was mystery till 1957, and it was explained by three scientists, Bardeen, Cooper, and Schiffer, in 1957, which is known as famous BCS theory. So this is the standard, this is the typical temperature versus resistance curve for superconductors. We see in case of non-superconducting, ordinary metals, the resistance goes down with temperature. And we see that at a particular temperature, the lowest temperature measured even at just at 0 Kelvin also, there is some resistance for these ordinary metals. Whereas in case of superconductors, the resistance becomes zero at a particular temperature called transition temperature. And this was explained how it happens. This was an experimental observation which was explained by this Bardeen, Cooper, and Schiffer, and they told if electrons form bound pairs, the pairs may behave like bosons, and many pairs can occupy the same quantum states. And so the electrons in superconductors bind into pairs, and these pairs condense into a single quantum mechanical state, which is explained by collective wave function. And they also got Nobel Prize in 1972 for this explanation. These are some of the graphs of resistance versus temperature for some samples which we have measured in our laboratory. This is an Nb3Sn superconductor which superconducts at around 18 Kelvin, and these are copper cladded. From the application point of view, some copper cladding was done on this. We got these samples from IPR, and it was again from Gujarat, Gandhinagar, Gujarat. A group is actively working on this copper cladded Nb3Sn and NBTI wires, and we measured this resistance for them. In our laboratory, we have prepared this VIBHA sample also. I'm just showing one typical photograph of, the curve for this. If you see in VIBHA, the superconductivity occurs at around 92 Kelvin, and we see a sharp transition and resistance following exactly to zero at 92 Kelvin. So another specific property of superconductors is Meissner effect, and which tells us an external field setups electrons on the surface of the superconducting material, and this in presence of magnetic field. In the superconducting condition, the presence of magnetic field doesn't affect these these magnetic lines of forces just go outside this superconducting sample. It doesn't enter in as long as it is superconducting. But of course, there is a limit to it. If we apply a very high magnetic field, it will penetrate through the superconducting materials. So an external magnetic field setups electron currents on the surface of these superconducting material, and these currents produce an equal and opposite magnetic field which cancels the external magnetic field inside this superconducting material. And this property is the source which has realized many applications and plays an important role in the development of developing the theory of superconductivity. So there are three limits to this superconductivity. One is the current, how much current is applied, and how much magnetic field can be applied, and the temperature. So this critical temperature, critical current density, and critical magnetic field, within this critical temperature, magnetic field, and current, the system superconducting material remains in the superconducting state. And the three hallmarks of superconductivity are zero resistance, complete diamagnetism, and macroscopic quantum effects, which defines the flux density. So for students, I have put one small video to show what is Meissner effect. So if you see, yeah. So we have a magnet here and a superconductor. This black sample is a superconducting sample. If we make this material, if in the normal state, the magnet doesn't affect this, it just falls around it. And if we make this sample a superconducting sample by pouring liquid nitrogen and bringing this temperature down below to this superconducting transition temperature, so you see this magnet the magnetic lines of forces cannot penetrate through this superconducting magnet. This is called the famous phenomenon levitation. So in the superconducting state, we see that the magnet is just floating over this. So now if we remove this magnetic field, now if we take this out and bring it to the room temperature, we see slowly the magnetic lines of forces will penetrate and the magnet falls. So this is famous Meissner effect. And this is a timeline for superconducting materials, how superconducting materials have evolved right from its discovery in 1911 to till date. So nowadays, a lot of work is going on in Phy-SU and very high temperature superconductivity. Through this journey, very high temperature superconductors have also evolved called VIBHA, mercury based, and sometimes there have been uses that superconductivity has been discovered at room temperature, but there are no such materials which can be easily made and can be utilized at room temperature applications. However, there are various important applications of superconductivity in superconducting computers, in MRI machines, in particle accelerators and research labs, in squids, and also they have promising future applications in high performance transformers, power storage devices, and electric motors, in magnetic levitation devices called bullet trains also. And there are 7 Nobel Prizes which this particular field has fetched. Right from Kamerlingh Owens to the latest one in 2016 to Kosterlitz, Hayden and Thouless, which has led to the discovery of even quantum materials. Another is interesting example is an example of some shape memory alloys. These are called smart materials, which are novel and special kind of materials which can remember their shape. I'm just trying to give you a flavor of some interesting materials so that you understand what low temperatures, how low temperature can manifest very interesting features of these materials. So they can remember their shape when heated above a certain transition temperature. They are also known as muscle wires or metal muscles, which can change and retain their shape with stress and temperature and magnetic fields. It was first these particular materials were first discovered by Orne Orlando as well as in Buller and Baum, and at different times. And famous shape memory alloy is called nitinol, nickel, which is alloy of nickel and titanium. So the specialty of these materials is that these shape memory alloys change their phase at different temperatures because of the atomic level changes. That means there is a rearrangement of atoms which takes place, and it happens because the arrangement of atom occurs at specific temperatures, and that is why the shape changes. And this is a typical optical micrograph of a microstructure of copper aluminum nickel alloy, in which we see that it has this kind of microstructure at one temperature. The twin boundaries occur, and the microstructurally the structural change happens in these materials. And we try to understand, and this happens at quite low temperature in most of the materials. That is how we try to understand these properties at low temperatures. So the high temperature phase of these materials is called the austenite, and these are actually solid phases only. There is no solid to liquid to gaseous transformation. It is a solid to solid transformation. That means microscopically the structure changes from either cubic to orthorhombic or cubic to tetragonal or monoclinic sort of this. So the martensite structure is a low temperature phase in which the system, the structure of the material changes to another structure in the form of these twin martensite boundaries or D-twin martensite phase. And the martensite state is relatively softer. And with temperature, it occurs like this. But with the, this transition is reversible. When we go back to the same temperature, it comes back to the earlier martensite structure. It is a displacive and first order phase transformation. So I would like to show you how these shape memory alloys are interesting, and this is a demonstration that how these alloys remember their shape. So suppose we have this spring, which you saw this phase initially, and we distort it by applying the stress on this. This was a austenite phase, and now we have distorted by application of stress on this. But if we apply, if we heat it again, it will come back to its austenite phase like earlier shape, which was a spring shape. So we try to heat it back and it comes back to its original shape. And if you try to do this experiment with the normal wire, you will not see this kind of effect, because this particular sample which you are seeing in the form of spring is nickel titanium, which is a shape memory alloy. So these materials can remember their shape. And they also have lots of applications. They have this, they are used in form of linear actuator, which are devices that develop motion from whatever available energy sources in the linear manner. The transformation in shape memory alloys occur either by mechanical energy or even temperature, and also by magnetic field. So it is an actuation kind of activity, where strain is typically strain developed is typically from 4 to 6%. So these shape memory alloys are used in the miniaturized walking robots also, and they are used in with the help of DC control system. This can be because they are able to generate the linear motion. So with the application of current or mechanical energy, they can have some motion. They are also used in space antennas also. This is a simple demonstration of shape memory effect in space antenna using nickel titanium wire. The antenna is in the deformed state in this initial figures A, B, and C. But when we send it to space with the help of the solar heat, they revert to its original shape, because it is difficult to send it in such a big big antenna in this form. So it is sent in the deformed way, and with the help of solar energy or solar heat, they get back to this shape of the solar antennas, space antennas. Sorry. And they are also used in biomedical devices also. Like one example is stent. It is nothing but a metal mesh. It is nothing but a tubular metallic device. Stents are the grafts which are used for the vascular applications. They are used to repair the damaged arteries, and also support the weak points in the arteries. So this is a typical photograph, how it looks like. This is a nitinol stent, and it is inserted inside the clogged arteries. They are also used in the to repair the broken and fractured bones. They are used in the form of bone plates wherever the fracture has occurred, in order to give a support to it. Also, they are used in many various electronic devices, and also wherever the shape change with a small mechanical energy is required, like in cellular phone antennas, in eyeglasses, and coffee pots, rice cookers. With a small heat energy, the mechanical change occurs. They can be switched off and switched on with the help of supplying a little temperature to it. So these are some applications for these materials. Now coming back to the most interesting materials nowadays, which are known as quantum materials. This is my last example, which I'll be describing, and we are doing currently research on these materials in our laboratory. So this is all the more interesting in current times, because Cabinet has approved this national quantum mission to scale up this industrial and scientific research for quantum technologies. to speed up our economic growth and leverage India as a leading nation in this particular area of quantum technology. So, as I gave an example of superconductivity, it is almost similar because both of them say that at a particular conditions, the resistance can be zero, because both of the requirement of the material is the resistance should flow without. I mean, the electron current should flow without any resistance or minimum resistance. So, what happens if electricity could travel forever without being diminished? We all know our electricity bills will reduce drastically, and we'll have very fast computers, exponentially faster in comparison to what we have now, and will be very perfect. They can have big calculations with perfect accuracy. So one is superconducting computers. One example is that. And what else? Because superconductors at present are not at room temperatures. And there are many other benefits also for the quantum technology if we have this kind of quantum materials. And of course, superconductors are also quantum materials. So what technology could build these abilities apart from superconductors? We would see in this few slides. So earlier we have to give you an introduction why we want to do this. Earlier we had this kind of big hard disk. In 1950s, we had the hard disk of the size of almost a full room, and it was very difficult to even transport them. But in 2004, we see we have very small hard disk. We have miniaturized to a very great extent. We can have, this finger size hard disk, which can be introduced into our small mobiles and other electronic devices. So hard drives work on the principle of, they store information in the form of bits. And we have this particular domains oriented in one direction, which are called 0 and 1. And that's how in binary codes, this data is stored. And with more sensitive sensors, we can have smaller bits, and hence we can have higher storage density. So this is the areal density graph per year, right from 1950s to current years, how the areal density has changed from in over these 45 years, right from few megabytes to few terabytes, almost of the order of 10 to the power 9 orders in these 45 years. So how it has happened, this is the thing, a simple miniaturization picture. We had very big hard disk and computers, and now we have slowly, in after 2010, in this 2000, in this century, we have these smartphones, laptops, and so on, embedded processors, which can, in a very small size, they can store a lot of information. So it was predicted by one of the computer engineer called Moore. He observed that the number of transistors in an integrated circuit doubles about every 2 years. So if you see from 1970s to 2005, this from megabytes to terabytes, every 2 years, this capacity capacity of these transistors inside the integrated circuit has doubled. But what we see after 2010 is this Moore's timeline for this future is coming to the end. You might have observed that after almost 2010 or so, we don't see much change in storage capacity. Earlier, we used to hear, right, when in 90s we had these big computers, and in early 2000 and before, and late 90s, we had this floppy disks and CDs, which could store up to gigabytes also. And later we had small hard disks which can even store terabytes of the storage, which have terabytes of storage capacity. But nowadays we don't see much improvement in that. This is because this has almost come to the end because of the heat dissipation in these confined devices. So what is the way forward? Because we are not going to stop here. We still need much more higher capacity storage. We every day, every individual has got number of photographs and number of data to store in their computer and in mobiles. So what is the way forward to enhance this storage capacity? The way forward is with the help of quantum materials. The answer is with quantum materials. What we call nowadays is topological insulators, or one of the examples is topological insulators and other quantum topological materials. So the interesting part is, if we can have the electronic transport from this type of chaotic road traffic to this kind of highway traffic, in which happens in ordinary metals, if we can have this kind of quantum topological materials where there will be no scattering at the edges and electrons can move with very high mobility, we can have this kind of, it is possible to have very fast computers and high storage devices. So this happens with the help of quantum topological materials instead of using this ordinary metals and semiconductor where electrons are in diffusive motion and have this kind of chaotic traffic inside. So if we have quantum materials, it is possible. But what it was first theoretically predicted, and the credit goes to these three Nobel laureates, Professor David Thouless, Halden, and Kosterlitz. They predicted this, and experimentally quantum materials could be observed in some of the interesting materials, which I will be describing to a small extent if I have some time. So just to introduce what are the quantum topological materials, we know the classification of solids, semiconductors, conductors, and semimetals in general. And insulators have this large band gap, semiconductors have comparatively smaller band gap, conductors have no band gap, whereas semimetals have this overlapping of bands. But in recently discovered class called topological insulators, they are actually insulating in the interior and conducting at the edges or surfaces. And none of this kind of band structure, they don't follow this kind of band structure, the standard for the trivial or the ordinary kind of solids. They are also solids, but they are insulating in the interior but have conducting edges on the surface. And under the right conditions, these topological insulators can even have perfect conductivity without resistance. And new type of transistor-based topological insulators can have potential to reduce the power used in computing and extend the advances in the information technology. So what is the difference between these topological insulators and ordinary insulators? To understand, this is a pictorial diagram which can be easily described on the basis of what we know about band theory and what we know as quantum Hall effect. So if we have atomic insulators, which are actually in these atomic insulators, we have these electrons revolving around these atoms. And these atomic insulators have this kind of band structure, when this conduction versus this conduction band and valence band, and this is the E versus K diagram of this. Whereas in case of topological insulators, they have their insulators from inside and conduction happens only at the edges. And how this is possible, this can be explained with the help of quantum Hall state. In the quantum Hall state, what happens? We have electrons rotating in the circular orbits in the presence of strong magnetic field. And because of this strong magnetic field and the circularly orbiting electrons, we have this discrete energy levels. Instead of this kind of energy states, we have this discrete energy states. Their band structure is a little different from the trivial and ordinary metals and insulators. So we have this kind of, the difference lies in this band topology. So the normal band insulators and quantum Hall states are topologically different. Topology is actually a mathematical term which was actually understood, which is actually studied in mathematics and theoretically explained, and it is now implemented on these topological materials. And the topology or the deformation of some phases is based on the distinction of this band structure. The topology of bands is different. So both the insulators have different band topology in the sense that they cannot be deformed into one another. If we explain this particular band topology of trivial band insulators in the form of this orange or spherical ball, the topology of the band topology of this particular quantum Hall state or this quantum materials would be something like this in the form of this medubada, or you can call it donut. So this differs in the in actually the external band structure. So if you see these two surfaces, they have two different band topologies. One is called sphere and another is donut. The genus, which is the topological invariant to define the shape of these bands, is 0 in case of trivial band insulator, whereas it is 1 in case of this quantum Hall state or quantum materials and these materials. So we define this particular topological invariant in the form of G, which is given by genus G. It is 0 for this and 0 for this topological insulators. So topological insulator describe the property of topology is the property which describes these materials, describes the property that which remains actually intact without deformation or stretching it. Sorry. So in case of topological insulators are actually quantum spin Hall insulators. They are quantum Hall, the quantum Hall effect without external magnetic field. Because if we have to apply such a strong magnetic field, it might be that they will not be useful at they will not be technologically useful. So there are certain materials in which this magnetic field is replaced by spin orbit coupling, which is inherent to these materials. So in these particular materials, we see because of this strong spin orbit coupling, the conduction band and this valence band, they are inverted, and because of this inversion, this surface states are formed. That means in what happens in the case of Hall effect. This is a case of this particular picture is the case of quantum Hall effect. When we apply a magnetic field at the edges, inside this, actually electrons start revolving in these cyclotron orbits, whereas at the edges they go in one direction. They only have one particular orbit, the right skipping skipping orbits. They keep on going in one direction, whereas at the other edge these electrons keep on moving in one direction, that is in the left direction. So this thing, which is this particular property, which is manifested due to strong magnetic field in case of quantum Hall effect, happens due to strong spin orbit coupling, and we see this inverted gap here because of this inversion of conduction band and valence band. And we see in case of normal crystal, it looks like this, whereas in the topological insulators or topological materials, crystals have spin and momentum locked surface states in the form of this like this. We have this spin momentum locked surface states. So the basic property of these particular materials, quantum materials, is spin and momentum locked surface states. So the key properties of these interesting materials are topological protection, they have linear band dispersion, and they have spin polarized surface states. And because of these interesting properties, they have no backscattering of electrons, and they have very high mobility of these charge carriers. And that is why these can be used in various potential applications in low power dissipation devices, devices with fast response time, spin electronic and magnetic devices. And the interesting example of these materials in are Bi2Se3, Bi2T3, Sb2T3, BASB, and various other nowadays. So, am I audible?
Yes.
Yeah.
Yes, ma'am, very well.
Can I continue for some time, or my time is over?
You can continue. No problem.
Okay. So I would like to give you some examples of our research. We prepare single crystals of topological insulators and rare earths, rare earth mononuclides in our laboratory, which show these interesting quantum mechanical properties, and because of which these materials are nowadays in a lot of, they have attracted a lot of research for the applications which are now being coming up. So these are the prototype topological insulators: Bi2Sc3, BISP, Bi2T3, Sp2T3. All these single crystals are grown in our laboratory. These are topological crystalline insulators, SNT, and some 2D magnetic materials, iron, germanium, tellurides, and some semi-metals and rare earth mononuclides, which show extremely large magnetoresistance. So this is extremely large. We have observed extremely large magnetoresistance of the order of 10 to the power 4, 43,000 percentage of magnetoresistance in this particular single crystal, which is antimony crystal, and it had some specific kind of defects which generated, because of the strong disorder which generated this high magnetoresistance in this material. And we analyzed this. It had the classical origin, which was explained in the form of Parrish and Littlewood model, and which says that in strong disordered systems where length scales of the inhomogeneities or disorder present in the system is of the order of their mean free path, and the observed MR is positive and linear in the form of in the form of spatial fluctuations in the mobilities. This was the particular case in this antimony crystal, and it had 43,000 percentage of magnetoresistance at 2 Kelvin and 9 Tesla, which is even larger than some of the known rare earth mononuclides like GDSB and LABI also. So having such a large magnetoresistance in such a simple, cheap material like antimony is very encouraging. And this crystalline, in the crystalline disorder in this particular material causes this carrier mobility fluctuations, which is responsible for this linear MR in this. So the accomplishment of such a huge magnetoresistance in such a low cost semi-metal like element, antimony element, could play a vital role in the realization of magnetic memory devices and magnetic sensors. So another example which I want to give you is from another rare earth mononuclide, that is yttrium antimony, YSB. This is the resistivity of YSB, and if you see, it has a large RRR ratio, which is actually the measure of how clean and good quality this crystal is. It is comparatively, this particular crystal of ours is very good quality. If you compare with other RRR samples from earlier published work. So in this particular work, it was we have measured this resistivity and found this magnetoresistance as large as 2 into 10 to the power 6 percentage. That is 20 lakh percentage, which was measured at zero magnetic field. So if you see, it has such a large magnetoresistance at 2 Kelvin and 9 Tesla, and it is because the origin is it has a large compensation. That means its number of electrons and holes present in this system is almost equal, and the mobility of these charge carriers is very, very high. These are few reasons which cause such a high magnetoresistance XMR in this material. So basically, very fundamentally speaking, this is a definition of magnetoresistance. If we can have large, to have this large change, we should have a large large resistance with the application of field and low resistance in absence of magnetic field. So if we have cleaner system, this particular ratio will enhance, and that is what is happening in our system. And another reason, important reason in these quantum materials is presence of topologically protected state, which we could see in this particular material by analysis of magnetoresistance data, which had very huge number of oscillations very large oscillations, very profound oscillations. When we analyzed them, we found this particular pi phase, which is an indication of having topologically protected state. And this is an indirect observation, the indirect way of observing this non-trivial band topology with the help of resistivity and this transport measurements. So this particular work is very important and has marked this this red particular mark shows that we have very high magnetic resistance in comparison to most of the known XMR materials already in literature. So if you see, except WP2, we have highest XMR in this particular sample. So there are other interesting signatures also which we could see in transport measurements, which can be seen in these topological materials. As I said, to observe the speciality of these topological materials, we must show that they have this surface state. This is what the presence of surface states distinguishes these quantum materials from the other ordinary materials. So these topological surface states can be observed in transport measurements by observing this quantum Hall effect, weak anti-localization effect, and presence of pi phase in SDH oscillations when we measure this resistivity in presence of large magnetic field. So we have done we have studied various crystals to observe these surface states in these quantum materials. And these are few examples. We characterize these materials thoroughly with the help of XRD, HR-XRD, SEM, and EDAX to understand how clean the system is and how good quality the quality of crystal we have. So in high quality crystals only these properties can manifest. So in the last example, I would give you this presence of quantum Hall effect in this Bi2Se3 single crystals. So we could observe these plateaus of Hall resistance, which are coinciding with the minima of these resistance. And we attributed this quantum Hall effect. We could observe this quantum Hall effect in this 3D system, because normally you know that quantum Hall effect is observed in two-dimensional systems. But we could observe this in our single crystals of 3D single crystal. And with this study, we can say that perfect 2D transport is not an essential criteria for the quantum Hall effect in this particular system. And this had large carrier concentration and few optimized enhanced crystalline effects. And this was because the quantum Hall effect in this particular crystal could be observed because of either weak interlayer coupling in the system and due to the formation of Landau localized states at the edges of the Landau level due to the presence of a particular disorder in this system. So thank you very much. Although I have many more examples, but I would like to stop here. And this was my introduction to various new materials and how we can study these important properties, which are very useful for the technological point of view through our simple resistivity, magnetic resistance, and Hall measurements.
Dr. Archana, you delivered a very, very nice talk on magnetic resistive materials, quantum materials, superconductivity, and shape memory alloys. So
Thank you very
our
much.
students will be benefited a lot from your expert talk. So on behalf of the organizing committee, I am very much thankful to you for sparing your valuable time for our students.
Thank you very much, sir. My pleasure.
Now the session is open for the questions from the audience. If there is a question, they may raise a hand so that madam can give the answer properly. Or you can ask also.
Thank you, ma'am, for the nice presentation. I have a question.
Yeah.
Since you mentioned that to get, topological insulators, they give out a very good percent MR. So may I know the reasons how the resistance increases in the presence of field in case of topological insulators?
Yeah. So as I said, in these particular materials, there are three origins basically which we could understand. Like there are various earlier prior studies in which there have been interesting magnetoresistance resistance has appeared, but not to this extent. In these particular materials, they have different band topology. That means the topology, the band structure is little different, which causes these materials to have very high mobilities. Not only this, the reason is the very high compensation. I mean, number of electrons and holes in these materials is very large. I mean, almost equal, and which causes these materials to have very high mobilities. So these are the basically three reasons which we have understood in this case. And most of these materials which are having different band topology have these large magnetoresistance.
Okay, so can we say that generally in case of metals where we have scattering or pinning centers, and because of which, as in we increase the magnitude of the field, then due to those scattering centers, the resistance, the increase in resistance is not that high as compared to the topological insulators where there's no scattering and
Yes.
the mobility is higher.
Yeah.
Thank you.
Anybody else? Any question from the students?
Madam, can I ask a question? I have been working a little bit closely to quantum dots, which are semiconductor nanomaterials which exhibit quantum confinement phenomena, but they are not primarily studied for their magnetoresistance or magnetic field study. Could you please throw some light as to why they are confined materials but still not part of the quantum materials?
Quantum confinement materials. What kind of materials you are talking about?
Ma'am, semiconductor nanomaterials, when the semiconductors are reduced to nanocrystallite size, they exhibit quantum confinement and discrete band energy states. And their band energy states are localized to discrete energy levels and they are categorized as quantum dots. But still, they are not evaluated and studied for their magnetic properties, and their applications are limited to optical domain. Could you please give a little
Actually,
highlight?
these particular materials, this kind of nanomaterials and all, most of the times this kind of it is difficult. This through this transport, we cannot study these transport properties in this kind of materials. For transport measurements, we require like a big rectangular shape kind of samples where we can have contacts and measure the. I mean, apply the current and measure the voltages. But in case of this nanomaterials, already this kind of things, we cannot make this kind of on particular one small sample, then quantum dot. We cannot have this kind of, we cannot do, these are experimental limitations. We cannot do these measurements.
So, ma'am, does it mean that we need a larger crystallite size to perform these
This
measurements?
particular transport medium, yes.
Ma'am, but is it possible that we can in future, is it a possible scope or research field where we can utilize or develop studies in this area?
To this particular, I mean, to have number of contacts at the nano level, it is difficult, but maybe with some future help of future technology, it might be.
Thank you, ma'am.
Anybody? If there is no question from the audience, then we can stop this. Madam, you can finish this.
Okay.
Excuse me, ma'am, I have no any question. I'm Narendra Jakhar. Your talk is very informative and you covered a large number of materials and provided a deep insight of magnetoresistance and single crystals. Thank you very much, ma'am.
Thank you, sir. Thank you very much.
Okay, one more time. We are very much thankful to Madam for sparing this kind of special time for our students. Thank you, Madam.
Thank you. Thank you very much.
Thank you, sir. Now I invite my fellow researcher Apeksha Maru to deliver the vote of thanks.
Am I audible?
Yes.
Yes.
Yes, you are audible.
Good evening. Good evening, everyone. Myself Pesha Maru. On behalf of Vigyan Yatra, I am here to give a word of thanks to our esteemed speakers. Thank you for sharing your knowledge, expertise, and passion with us. First of all, I would like to thank Dr. Narendra Jakhar sir for giving very brief and informative information regarding X-ray photoelectron spectroscopy, which gives surface information through the probe. We are very thankful to you, sir. And I would also like to thank our second speaker, Dr. Archana Lakhani ma'am, for giving very interesting information about the magnetotransfer studies that involves resistivity, magnetoresistance, and Hall effect via quantum materials at the interfaces of physics and technology. Thank you very much, ma'am, for showing us the facilities available for this type of measurements. Thanks again, ma'am. I would also like to thank Chief Patron, Professor Nilambari Dave, ma'am, Professor Chaitanya Joshi, sir, patrons, Professor Girish Bhimani, sir, Dr. Narottam Sahu, sir, co-patrons, Dr. Raji Parmar, sir, Shri Vivekanand Pai, sir, and Professor Atulem Gonsai, sir. I would also like to thank conveners of GVS 2024 and event coordinators, Professor N.A. Shah, sir, Professor P.N. Joshi, sir, Dr. Jirin Pandya, sir, and Dr. David Dhruv, sir. Apart from this, I am very thankful to Vigyan Gurjari and GUJCOST for managing the conference series. I am very thankful to all the participants present here. I would also like to thank the press and media for their wider publicity and outreach of this conference. So we are ending today's session. Next, we will meet for the next session on the Monday, 11th March at the same time. So thank you very much. Have a good day, everyone.
Thank you, Apeksha. And she is sitting in my lab right now. You all
Yes,
can
ma'am.
see the laboratory also. This 9 Tesla PPMS system on which we had shown most of the measurement is seen behind her.
Yes, ma'am.
Nice.
Thank you.
So
So
today's
can we
board
log
of
out?
women, very nice talk.